Okay, we should be recording. So I'll just say again, welcome to the Bayes 2023 Southeast Area Stats Workshop for the recording. Oh, and let me assign Amanda as a co-host. Thank you, Amanda. Okay. So now let's basically what we're going to do today is we're going to start with kind of a brief lecture, giving some background on what Bayesian statistics is, why it's cool, why it's an important tool in your toolbox. It's not a perfect cure for everything, you know, what it can and can't do. We'll go over that for the first, 4 to 5 minutes or so. Obviously, any Q&A during the time, and the rest of the time will be a hands-on demo where we're going to go through examples. I'm going to go through examples, but before we actually start the R stuff, I did want to go through with you how to get it set up in case you have not. So once again, I'm going to, in case anybody couldn't see it in the chat before, I will post the link, the invitation link in the chat if anyone hasn't signed up yet. And now I'm going to share my screen and show you how you would go about setting up your workspace. And by workspace, that's basically a pre-created environment with all the packages already installed and all the data already there that you're going to need to follow along with everything today. So to save you the trouble of having to configure your own machine. But of course, this is only approved for demo use, and you cannot upload any government-owned data or do any of your own real analysis on this server. This is only to be used for this class. So thanks for your understanding there. Anything after, I'm happy to help you set up all this software on your own machine. So everybody should be able to see that. And so, yes, so if you join Deposit Cloud workspace, you'll be in this December 2023 Bayes workshop. You won't be able to see all these other projects. Those are, I can see that because I'm the admin. Now, once you join it, you're going to create new project from template using this, this link at the upper right drop-down menu. Once you click on that, it'll pop this dialog up, and this Bayes workshop template is what you should select. Hit OK. And it will take a moment or two to load, but let me just do that to make sure it works from my side, because I'll be running everything from this as well. Okay, and yes, so you should have an R terminal, and the first thing you should do when you get in here is in the Files tab, you see the worksheet for the course. If you click on that, it'll open up the script, and you'll be able to see everything there. And as we go along, the way that I like to do this is all the code is here, but some of it is missing important parts. You have to fill in the blanks with these ellipses, the 3 dots. Every time you see those, delete them, and we'll replace them with code as we go. And I think that's a great way to learn, because if I gave you all the code, you would just be able to blindly copy and paste. If I gave you none of it, it takes forever to follow along, and you'll make typos getting caught up. This is kind of a nice compromise. You get a little bit of muscle memory typing in some stuff, but you won't fall too far behind. And just as a reminder, if you go to the main course page, the lesson is available in text form. And let me just show you that, actually. Let me go ahead and show you that. It is at the SEA Stats, let's see, yeah, SEA Stats page, Bayes Workshop 2023. You go to that page, happy holidays to everyone, and the course materials, lesson text right here. Oh, and if anybody is doing this not on their own, not on the server, but on their own machine, the worksheet is here for you to download. The slides I'm going to be showing you are also here for you to download if you want them. And here's the text form of the lesson. It's all here, and basically everything we're going through, the lecture is all written out in prose. And kind of giving away my memes here, but yeah, all the code is in here, so you can copy and paste it off of this if you follow along with that. Okay, that's everything from a logistics standpoint. Does anyone have any questions right now on that? Okay, great. So let's go ahead and start the exciting and fun lecture part of the course where I tell you everything about Bayesian stats and how cool it is. Okay, just 1 second here. Okay. And again, I would love for folks to ask questions as we go if you don't understand anything or need clarification. So yes, so okay, the name of the course is a crash course. So we're doing stuff that's kind of like a semester's worth of content in 3 hours. You know, I'm going to gloss over some stuff and miss out on some details, but I encourage you to study this up on your own or ask me later about some of the details, technical details that I by necessity must skip because we only have a short time for this. Bayesian, we're going to understand what that is. You're going to be completely literate in that in just a few hours. Mixed models, like hopefully most of you have at least seen or heard of mixed models before. I'll talk a little bit about that. And brms is the modeling package in R that we're going to be using. So it's going to be a brief and practical introduction to fitting multi-level. That's another term for mixed models in R and Stan. So R is kind of the interface we're going to use. Stan is the engine that's going to be fitting the models behind the scenes. And yeah, I'm going to give you a quick intro to Bayesian, but the focus is going to be on the practical skills of it. I would love for folks, like I said, to have had a bit of experience knowing what mixed models are. It's helpful if you've at least heard of Bayesian stats. Yeah, part of the reason I do this isn't necessarily so that people can go out there and immediately fit all the Bayesian models themselves. You're all scientists. This is an important statistical approach that is just becoming more and more common. If you review a manuscript, you might see it, that kind of thing. So it's good to be literate in it, even if you don't go out and do it. And I put in some advanced prerequisites. BRMS is patterned after the R package LME4, which is used for fitting non-Bayesian mixed models. It uses the same syntax. So if you've already used LME4, you'll find it very easy to use BRMS. If you haven't, that's still okay, because we'll go over it all. And we're going to use tidyverse and ggplot2 packages for some of the, manipulation of data and making some plots and stuff. So you don't really have to understand that part of it, but it would be helpful for you. You'll be able to follow along better. Okay, I already went over this. I showed you the slides and text, how to fill in the worksheets with ellipsis and where to copy and paste from if you get stuck. And I'd like to go over the learning objectives. This will all seem like nonsense to you right now, but hopefully you'll understand it soon. We're going to go over the basics of Bayesian, of inference using Bayesian statistics. We're going to talk about priors, likelihoods, and posteriors. You might have heard those words before. We will try to demystify. We're going to go over a little bit of Markov chain Monte Carlo, which is the algorithm that you use to sample and estimate the parameters of a Bayesian model. And we're going to talk about credible intervals, which is how we estimate uncertainty in our parameters. Again, we'll go over all this as we get to it. Those are kind of the conceptual learning objectives. In terms of practical stuff, we're going to be writing code to fit a multi-level model, random intercept, random slope model, how to help get models to converge, how to interpret the output, compare model. I'll just go through this real quick because we'll go to it all as we come, and different ways to test hypotheses, assess strength of evidence, and how to plot the predictions we make. All general stuff you'd want to do with any statistical model, but we're going to do it in the Bayesian style. Okay, what is Bayesian inference? First of all, who is this old white dude? Well, some people say it's a portrait of Thomas Bayes. It's actually not known for sure whether this is Thomas Bayes or not, but this is always the picture that people show. when you're trying to show Thomas Bayes, but it's some old reverend from around the same time that Thomas Bayes lived. It might be him, it might be someone else, but this is the picture they always show. So I'm going to join in that long tradition and show this really awesome, engraving of Thomas Bayes. Well, he lived around 250 years ago in England. And so what is Bayesian inference? Well, it is a method of statistical inference. So using data to make some conclusion or learn something. And what is special about it is it allows you to use information you already know about the world to assign a prior probability to a hypothesis, how likely you think something is to be true before you see the data, and then use information to update the probability of that hypothesis. So before we have a model, before we see the data of the world, then we get some data, we update our model of the world based on that data we got. And I'll continue to hammer that point over and over. And it's really not just for statistics. This approach is used in many disciplines and fields. It was used Bayesian approach of updating models with data is used to locate wreckage of plane crashes and decide which area to go search for, search the ocean floor and that kind of thing. Yeah, it's used in many disciplines. We want to use it to estimate parameters of statistical models. That's just one use for this approach. And this approach has been around, since the time of Thomas Bayes for hundreds of years, but it has not been used practically until probably the last 20 years, since hardly anyone used it before 2000. And that's because the computational ability to do it was not there. And that has really happened in the last few decades. And then really in the last, 10 years, more user-friendly software has been developed so that you don't have to write a whole bunch of code on your own to do it. It's kind of making it easier for people who aren't, able to just crank out reams of code to actually fit Bayesian models. So, there's never been a better time to go Bayesian. So it's great that you all are willing to go with me on this journey. So we're gonna start with the very basics of Bayes' theorem. There's this famous picture of some office where somebody made a neon sign at a Bayes theorem. It was developed independently, both by Bayes and by pretty well-known French scientist named Laplace around the same time. But for some reason, even though Laplace did more with it, the Bayes name has stuck. We'll talk about Bayes' theorem now in a bit more detail. Okay, so it's, if you read that out in probability notation, the probability of A given B is equal to the probability of B given A times the probability of A over the probability of B. That's how you would read it out in English. That doesn't make a lot of sense, but what does that mean? It is how likely an event is to happen, or how likely a piece of data is based on our prior knowledge about conditions related to that event. So it's the conditional probability of event A occurring given that event B occurred. So conditioned on the probability that event B occurred. I'll give some examples to help you understand that. So another way of saying it is the probability of A being true, given that B is true, the probability of A given B, is equal to the probability that B is true, given that A is true, times the ratio of probabilities that A and B are true. That's another way of saying it. Again, that still is very abstract, and let's talk about it in the context of our statistical model. So A is our statistical model. It's a hypothesis about the world. It could be, a statistical model could be the slope and intercept of a regression line. That's A, that's a statistical model. So how probable is it that our hypothesis is true? The P of A in Bayes' theorem is the prior probability. That's the prior probability we assign based on our subjective knowledge before we get any data. We have to have that to put together all the pieces of Bayes' theorem. Okay, we've got our model in our head, you know, we think maybe there's a relationship between some stuff. We have to go get some data to see, since we're scientists, we want to empirically verify by getting some data. We go out and collect some data. B is the data, observations of X and Y, for example. And the probability of B given A is the likelihood. That's the probability of observing that data if our model A is true. So like if you hypothesize prior that there's a positive relationship between X and Y, and then your data show a negative relationship, then the likelihood of observing that data if the model A was true would be very low. Like by chance, you probably wouldn't see a negative relationship if there really was positive. So we use the likelihood to update our estimate of probability of the model, and then we get probability of A given B. That is the posterior probability that our model is true, given that we observed the data B. And so that posterior is our new estimates of the parameters. We have new estimates of the slope and intercept, or whatever it is, after we've gone out and collected the data. Any questions? All right, it's very dry. We'll try to spice it up shortly, so with more concrete examples. Well, but before I do that, we'll finish the last piece of Bayes' theorem, probability of B. That's marginal probability, the probability of the data. But I won't focus on that because basically all that is a normalizing constant, because all probability distributions have to integrate to one. So it's basically just a normalizing constant to ensure that that both sides are equal to each other. And if we're comparing two models with the same data, those will cancel out anyway. So we typically, at least for now, we don't have to worry about it. So let's restate Bayes' theorem again. The probability of the model given the data is proportional to the probability of the data given the model times the probability of the model. And that's the posterior is the likelihood times the prior. So basically what we believed before about the world, before we got our data, that's the prior, times how much our new data changes our belief about the world, that's the likelihood, equals what we believe now about the world after we got the data. So what we used to think times some data equals our new ideas about the world, because data, we learned from the data to change our beliefs about the world to something that is more in line with reality because we got the data. Does that make sense to everyone? Hopefully. That's kind of like the elegant underpinning of Bayesian statistics. Okay, so let's do an example of a very, 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 very simple statistical model that only has one parameter. It's like the easiest statistical model you could have, which is we go out and find a coin lying on the street. And okay, what is a good prior on the probability of getting heads if you were to flip that coin? Anyone want to take a stab at that? 0.5. 0.5. Okay, that's a great prior. Okay, let's go get some data to test that hypothesis. Well, you flip the coin 10 times. 8 times, it's heads. Now, what do you think? Is your statistical model, without doing any formal math, would you change your statistical model that the probability is 0.5 if you observe 8 out of 10 heads? You would. So you think that coin actually has an 80% probability of heads. So you might. Okay, see, that's legitimate. Some people might say, well, you got that, 8 out of 10 was a chance result. It still has a high enough likelihood of happening, even if the true probability was 0.5. There's still a fairly high likelihood of observing 0.8 heads in a small sample. So some people would say, well, we don't, yeah. Some people would say you would keep the probability, your posterior estimate still around 0.5. Okay, but let's say this guy from a YouTube video I found comes up to you and shows you a coin, okay? And he offers you a game. He says, well, I'm gonna flip this coin 10 times. I'm gonna pay you $1 every time I get tails, and you pay me $1 every time I get heads. Okay, and you say, sure, why not? And you start to play. And well, first of all, what would your prior be on the probability of heads in this case? It might be higher than 0.5, right? Because why would somebody offer you that proposition unless they thought they would probably win, right? So your prior might be a little bit higher than 0.5. Then you play this game 10 times, 8 times, the coin comes up heads, only 2 times it comes up tails, just like in the coin we found on the street. Well, what is your posterior estimate now? You got the same data as the other time, 8 out of 10. Anyway, the thought I had there was that maybe your prior was a little bit more slanted toward high probability of heads, so your posterior estimate is also going to reflect that because of the subjective belief we had that this is not a fair game to begin with, where a random penny off the street is probably not rigged, you know, to be unfair. So that's pretty cool that we can incorporate that into the analysis in a Bayesian framework, because in a classical frequentist, what they call frequentist statistical model, you cannot incorporate prior information into the analysis. In every case, the maximum likelihood estimate of the probability would be 0.8, no matter what. Even if you only had 10 coin flips to go off of, you have to throw away all your prior knowledge about coins that they tend to have a 50-50 chance and say, well, even if there's a high confidence interval, the mean of it is still 0.8, because all we can use is the data we have in front of us right now. We can't use any prior knowledge. We're freed from that constricting and unreasonable and unrealistic rule when we use Bayesian analysis. So I thought this was a good time to kind of talk about probability a little bit and how it is interpreted by Bayesians versus frequentists. Frequentists being like the t-test, ANOVA type of statistical models that you are probably familiar with. So there's a key difference in how they interpret probability. A Bayesian probability includes how uncertain an event is in our knowledge before it happens. So like, let's say before the 2016 Olympics happened, I said, okay, I really think Usain Bolt has a high probability of winning the 100 meters gold medal. He probably has a 75% probability of winning that race. Well, frequentists cannot say that. You cannot have a probability of a single event, right? Like in retrospect, he did win. It makes no sense. You can't really say what the probability was, because either he wins or he loses that one race. There's either happens or it doesn't. That's frequentist probability. In frequentist analysis, you have to say probability in terms of a long run frequency. Like for example, if you hypothetically ran that same race many, many times, you could say Usain Bolt would win 75% of the time. But you can't really say his probability of winning one race is 75%. But Bayesian probability can. We also can incorporate our imperfect knowledge about the world and see that one single event as an uncertain outcome before it happens. And Bayesian probability is giving a number to that belief that best reflects the state of our knowledge at the time that we assign that probability. Any questions on that? Anyone? Does that make sense to everyone? So that's Bayesian probability. Now, here's the problem. That it works great for coin flips because you have one parameter. But anytime you have a real statistical model, there might be a lot more than one parameter. Plus, there's a lot more data than just 8 and 2. It's, you know, whatever thousands of rows of data you have. So usually the probability of the data is an integral with many, many dimensions. Every parameter adds another dimension to that integral. Now, you know, like for example, if you have a mixed model with random effects for blocks or something, every block's random effect is an extra parameter in the model. Every slope, every intercept, you know, even a fairly simple model could have hundreds of parameters. If you know from calculus, even doing a 2-dimensional or 3-dimensional integral is you can't really hardly do it by hand. So you're definitely not going to be able to do hundreds or thousands of dimensions integral. It just wasn't possible to do Bayesian statistics in the way we would want to for many years. And that's why it wasn't really done in the time of Bayes. It only has been started recently. So luckily, about in the, you know, 50, 60 years ago range, some very smart people came up with an algorithm called Markov Chain Monte Carlo, MCMC. That is a kind of algorithm that samples from a probability distribution, like the probability of the data that I just mentioned. It is a chain because it samples many times, and each sample depends on the one before it. So they chain together. Now, the longer that chain runs, the closer you get to the right answer. And that's how we are going to use MCMC algorithm to estimate the parameters of a Bayesian model to sample from that probability distribution. And usually the way we do it is, and so Markov chains have to start at one place and then eventually they make their way to the right answer. So the way we do it in Bayesian inference usually is do multiple chains that start in random places, and once they all kind of get to the same answer, regardless of where they started from, we can say, well, that's probably the right answer. And then we get rid of the first few samples because you don't want it to depend on where it started from. That's the warm-up. And what is left is our estimate of the posterior distribution. That's how we're going to do it. Now, and in the late 80s, early 90s, some quantum physicists came up with a really even better MCMC than had ever been made before, called Hamiltonian Monte Carlo. And it is the fastest and most efficient algorithm of its kind that has ever been developed. And it's very cool. I won't go into the details of how it works because I hardly understand them anyway, but it works really well. It gets to the answer so fast and compared to other ones in the past. And it is implemented in software called Stan. And actually, it is a lot of SAS also has a HMC procedure, proc B glim. So it's not just for R and Stan. MATLAB also has one. A lot of statistical software now uses HMC because it just works so well. So you don't have to, yeah, you can do all this in SAS as well if you want to. Now, Stan is the software that the HMC runs in, but it's kind of hard to write your own Stan code because you have to learn a whole new programming language just to do it. But about 5 or 6 years ago, a guy named Paul Berkner developed a package called brms for R, and it makes fitting the models using Stan way easier because all you have to do is write your model specification just like you would write an LME4 one in R with basically one line of code. Behind the scenes, it sets up the whole Stan program for you, runs it, samples the model, and brings you the result back. It even does a lot of the work of setting up the prior distributions for you and does all these computational tricks to speed up the Monte Carlo convergence and give you the right answer. It's a great tool. I use it pretty much every day. That's what we're going to use today. So the last kind of lecture-y stuff I wanted, well, first, are there any questions here? Please feel free to jump in the chat and ask a question or unmute if you have a question. I'll just keep going, but feel free to interrupt. So the last kind of lecture part I have before and then maybe we'll take a short break after that, and before we start the hands-on stuff. I want to just go through some common misconceptions and myths about Bayesian inference and try to bust them one by one. So the myths are Bayes is confusing, Bayes is subjective, Bayes takes too long, and that you have to either choose Bayesian or not. You can't do both. Those are kind of all of which I think are not true and are common misconceptions. So, okay, let's bust the myth that it's confusing. Well, yeah, sure, it is a little bit of a learning curve. I won't deny it. And but I think part of the reason is that because most people have done most of their training in undergrad and grad school using only frequentist methods, so this is going to be new to you and unfamiliar. But it's no more so than any statistic approach would be if you learned it from scratch. And I think people are now have second nature some of the confusing aspects of classical statistics, that they don't question them anymore and think about how confusing they are, like the focus on rejecting null hypotheses, which are not anything that conforms to reality, and frequentist statistics require you to imagine a hypothetical population that may not exist to calculate long-run frequencies of events. That's actually kind of hard to wrap your head around too. And if you just do it a lot, you get the hang of it, just like the Bayesian stats as well. Okay, so is Bayes subjective? Shouldn't we be like Vulcans, have no emotions, and not put any of our subjectivity into what we're doing? That is, R.A. Fisher, who developed most of the frequentist methods, really strongly felt that Bayes was subjective. He felt it so strongly that he went on sort of a campaign to discredit Bayesian methods, and it worked because no one did them again for 50 years after him, because everybody respected what R.A. Fisher said. But I think that he was wrong, because there is no such thing as a perfectly subjective. Vulcans do not exist. All statistics is done by human beings, and all approaches that you would do make assumptions and require prior knowledge. The better part about Bayesian analysis is it helps you be explicit and formal about how that knowledge is being incorporated into your model, instead of trying to pretend like it's not. And I think it's actually not a bias, it's actually a benefit to be able to put some of that prior knowledge into your model. And in my opinion, selectively ignoring prior knowledge and pretending it doesn't exist can be seen as just as bad as cherry picking data to put in your analysis. Either way, you're throwing away information that is true and that exists. So yes, that's my take on it. Not everyone, this is actually somewhat controversial. Not everyone agrees with me on this. You can read, the debate kind of has died down a little bit. It's started to resolve itself, but for decades, the debate was raging about this, in the lit. Okay, well, fine. If you agree that Bayes is not too subjective, some people say, well, I can't do it because it takes too long. Yeah, that's kind of only sort of busted, because yes, it does. It is computationally intensive. The models take a lot of computational time and resources like memory to run. Well, there's two ways around that. Number one, get really, really fast algorithms for Monte Carlo sampling that are very clever and help you converge on the correct solution using a minimal amount of computing time. That's kind of the approach that we're taking today. There's also a whole other set of algorithms that approximate the solution of the integral without doing the Monte Carlo sampling. And there's a R package called INLA, where it's a software package that has an R version, but it exists outside of R as well, that takes that approach. And it's a very cool package. I would recommend looking into that as well. So those are kind of the two ways you can work around the computational roadblock. Finally, okay, you can't be both Bayesian and frequentist. You have to pick one approach or the other. It's like a religion or whatever. You can't be both. Well, I don't agree with that. I think that these are not dogmas that you have to follow like it was a religion. They should be tools in your toolkit. It is great to have the ability to do all of it, the differences are kind of exact. I've kind of focused on the differences just to teach you, but the lines are blurring now between what is Bayesian and what is frequentist, because, you know, even if you're not Bayesian, a lot of people use model selection. A lot of people use cross-validation. People use penalized or regularized regression. Those are not Bayesian techniques necessarily, but they have very similar effect to the use of priors. They constrain our estimates based on something other than what's in the data. So they kind of do the same thing in a way. And like, especially with machine learning techniques, the boundaries are really blurring, and it doesn't even make sense anymore to say I'm Bayesian or I'm not Bayesian. Like, it's all tools in the toolkit. So I'm hoping to help y'all learn a new tool today. So yeah, that's, oh yes, I have, I think, one more slide here. Another important motivation for using Bayesian statistics is some models just do not work without a Bayesian approach. The computational algorithms for maximum likelihood will not give you any answer for certain sort of complicated mixed models. Well, if we can add some priors, that stabilizes the computational algorithm and helps you get the correct answer faster and better. So that's kind of like a practical reason. Even if you think all this prior stuff is bull, you might still want to use it because it helps you. It just helps from a computational standpoint to use the Bayesian approach. And another nice thing is sort of the philosophical benefit is, instead of focusing on this yes or no, accept the null hypothesis or reject the null hypothesis, it focuses more on estimating effect sizes, how big they are, and what is our uncertainty. Sometimes I think that is a better way of looking at problems. And the probability has more direct interpretation too. If you get, you can say with a Bayesian analysis, the probability that our parameter is between A and B is 95%. You can't really say that with a frequentist analysis. You have to say, if we hypothetically ran this experiment many times, our estimate of this mean or this parameter would be between A and B 95% of the time. People don't really think about that, but that is actually what you're saying when you have a 95% confidence interval from a classical statistical perspective. But the Bayesian interpretation is much more direct. The probability of this parameter, of this difference between two means being between A and B, is 95%, you can say. Okay, so that was my very boring lecture part of it. Let's have Q&A for a couple of minutes, then we'll take a 5-minute bathroom break and kind of start the hands-on part of the class. So if anyone, feel free to unmute or post something in the chat if you have a question.
I have a question.
Yes, Raven.
Do you have an example of, because you were saying some models can't be fit with the frequentist
Yes.
methods. Do you have an example of something
that comes up a lot with generalized linear mixed models that have, so that would be like ones that have non-normal response distributions that have sort of a complicated random effect structure, like with repeated measures or something. Those just, the computational algorithms sometimes don't work. Or a lot of times, if you have outcomes, this happened with some of Cassie's stuff as well, like if you have a binomial, like a binary data, yes or no, like disease or not disease, and in some of your treatments or in some of your blocks, you have 0% or 100%, you have no variance within that treatment. Like if every single individual in one of the treatments got the disease, you can't estimate the variance. The maximum likelihood algorithms die and just fail on that. Even if like it's only 1 out of 20 treatments, it'll mess up your whole model. So the Bayesian approach will let you put prior information in and say, well, if 100% of individuals in this treatment got the disease, the prior probability is probably like kind of on the higher side. So you can add that information in to help it converge. That would be, yeah, that's kind of a general class of examples of where that would happen. Thanks for the question.
Nice.
Dr. Reed, you have a question in the chat about
Yes,
computational requirements?
Let's see. I see. So here we go. We have a lot of questions here. I'm scrolling down. Okay, so someone asked about sort of a more hardware-like question. What kind of RAM or CPU cores do you need on your machine to run these Markov chains? Well, that's a great question. And typically the recommendation is to run 3 or 4 Markov chains. So like, let's say you had, yeah, just think if you want them all to reach the same answer. If you only run one, you have no way of knowing, even if it stabilizes on an answer, if it's right, because it might have gotten to a local maximum somehow and got stuck. If you have 2, that's getting a little better if they get to the same answer. There's still kind of a chance that it's not the optimum, that it's like a local optimum they got stuck at. 3 or 4, okay, like if you have the odds that they all reach the same wrong answer are starting to get low. So like usually 3 or 4 is what people recommend. When I was in grad school, I only had a 4-core laptop, so I had to keep 1 core free to like, you know, browse the internet or whatever. So I only ran 3 Markov chains usually. Now that I'm, you know, a pro, I have an 8-core laptop and I can run my 4 Markov chains and still have 4 cores free, because any more than 4 is a bit overkill. Like you probably don't need too much more than that unless you have a really complicated model. And yeah, it does sometimes take a lot of RAM, but I run these, most of the models I can run on the laptop in, you know, minutes to an hour or 2 at most. Anything longer, I do have to sometimes run it on Scinet, and that, you know, the cluster 1632 gigs of RAM or something, but never too much more than that. So like it mostly for stuff you're going to do, you can mostly do it on your own laptop. Let's see. So somebody commented, it would seem we use Bayesian methods all the time to make decisions in life. That's a common thing you hear, that Bayesian statistics corresponds more closely to how people's brains actually work, and that like it's more intuitive for that reason. I don't really have a strong opinion on that, but yeah, you will see that a lot. How would you recommend in using Bayes analysis of biological events dealing with unknown priors or highly correlated priors? Well, yes, right. It's not always the case that we would want to put in very, very specific subjective information about a parameter estimate. We might not know. But a lot of times in practice, a prior is more to just constrain the values to something that's plausible, you know, that the effect size is not, you know, our outcome increases by 1 million with every degree of temperature increase. It's just to constrain it to like order of magnitude to help the model converge faster. Those are called weakly informative priors. And that is what, at least what I do 90% of the time, it's just a weakly informative. You don't really know anything. You're just constraining it to something that's like plausible from, you know, that it's not going to be, the parameter is not positive 10,000 or negative 1 million or anything like that. Let's see. So, yes, people are discussing probability as well. Yeah, I think we've covered the coin flip example plenty, so I won't go into that anymore. But let's, since we've now reached a good stopping point, let's just take a break and resume at 9:55 Eastern, 8:55 Central, and we'll do the hands-on portion at that time. So I'm just gonna go ahead and mute this side of it so we can take a quick break. Oh, I do see some more questions popping up in the chat, so I'm just gonna try to address those. Somebody asked, Somebody's asking if Bayesian statistics is more compelling with small data sets than frequentist statistics. Yes, that is,
Quentin, you
hey,
have
I'm sorry. I just put it on mute so that I can, someone else asked a question. Sorry about that. Somebody's asking if Bayesian statistics works better with low or small sample sizes. Yes, I would say that is thought of as kind of like the best use case for these things because, you know, it's computationally intensive, so you don't want to have like big data in the sense that they use it now with like billions of data points. You're going to have to use a more approximate approach. And but like for our small experimental data sets, yes, it works well. And because of the fact that you can use the priors to constrain the parameter estimates, it can help you because in your small sample sizes, that's where you're going to get things like no variance in the treatment because all individuals had a certain outcome. Then it will, yeah, it's great for that. Okay, so let's see, still unsure about the answer of the priors as I work on biological events most of the time that are additive with hundreds of priors that are weak. How can we use Bayes to deal with this in a better way? Yeah, so I think that is kind of you would want to assign if you have hundreds of additive events, you would want to assign a very, very narrow prior to each of those. If you think you have hundreds of weak of effect sizes, most of which are weak, you would want to assign a very narrow prior. Now, one thing you could do is do something like assign a t distribution to the prior. A t distribution is like a normal distribution, but it has extra mass in the tails. So it's like we have a high probability of a small effect, but we're still allowing for that possibility that occasionally one of your hundreds or thousands of markers or whatever has a big effect. So if you construct the priors in such a way that most of it is a weak effect, but you still have some probability in the tails of the distribution, that will work well. I don't know, Lena, if that answers your question. I mean, we can talk more specifics later about your particular use case if yep. And we're also having some technical questions which I think my TAs are dealing with. So I'm going to go to the restroom real quick and be right back and resume in 3 minutes. Okay, I think in just a minute or two, we will resume. Hopefully, everybody is at least getting the workspace fired up. Yes, I see, I want to introduce I forgot to do this at the beginning, introduce Grant Billings, the teaching assistant, who is helping with things, but he has stepped away, so we'll have to wait just a minute to give him that big, warm USDA welcome. Let's see, but meanwhile, let me get everything started here. Okay, yep, so yeah, we're getting right into the coding here. So yeah, what we're gonna do, close that. Okay. So, everybody hopefully has figured out how to join the workspace, or you have this going on your own machine, which is great. I think the majority of you don't. So yes, once you start the new project from template, following the instructions on the website, you'll have this cloud space going, and then you'll open the worksheet. So you should see what I see. Oh, yes. Oh, and Grant is back now. So I forgot to do this at the beginning. I would like to just thank Grant Billings, who is the teaching assistant today. He's a grad student here at NC State University, and also works with the GBRU unit. So yes, I appreciate his help with the technical aspects today. So yes, thank you very much, Grant. And yes, so here we go. Let's get started. So from now on, I'm kind of gonna switch back and forth between my console here and the slides as we go. So the first thing, now on here on the workspace, everything is installed. So what you're gonna do is you run the code. If people are not familiar with RStudio, I'm not gonna go through it too much today, but this is the terminal or the console where you can type in individual lines of code and run them by hitting enter. But this worksheet is basically an R script, and you can run code directly from the script. If you have your cursor on a line and hit Control Enter or Command Enter, if you're on a Mac, it will run the line. Or you can highlight with your mouse a block of code and then hit Control Enter, which I'm going to do right now, to run the code. And this is loading all the libraries and packages that we need to run everything. There's a lot of warning messages, but we don't have to worry about any of them. Everything loaded. So this is just like every time in R you start a new session, you have to load the packages, which are the libraries of code that is needed to do the analysis we're going to do today. And I have them all installed. So install is when you do that once and it puts the code on your machine. I've already done that on the cloud workspace. Loading the library is what you do every time you start the session. Okay, and this here, let's see, did I put that? I may have forgotten to put this in the. Yes, here I put it out of order. No, it's not, I didn't put it. Oh shoot. Okay, if you're gonna need to, I'll put this in the chat then, since I neglected to put this in the worksheet. If you're on the cloud server, you're gonna need to set the path to Stan, which will allow R to find the Stan software. So I'll put this in the chat. I'm sorry, I forgot to put this line of code in the worksheet. I apologize for that. So I put it in the chat. You'll have to copy and paste that. Sorry for people who are local. You'll have to just type that in. Apologies there. So yes, I'll just paste that here, and then I'll run this line of code with Control Enter. So now it knows where to find the Stan software. That was just an issue that came up creating these workspace templates, that it had to do that. Everyone good? Okay, now, you can run the next couple lines of code, which will set the plotting options, and this one will create a data for the fit model object, which already exists here, but in case you're running it on your own machine, it will create a directory to put fitted model objects in. If anybody gets stuck, please interrupt me, or put something in the chat, and Grant will help you in a breakout room. We'll do our best to keep everyone following along, which is hard with so many people participating. Okay. And now these are the options for BRMS model fitting. We're going to use the options function to set the backend to command stand. So we're going to just assign, this shows what backend model fitting engine will be used to fit the models. MC cores, actually this won't do anything on the workshop, the workspace, because we on this cloud server you don't have access to 4 cores. But if you're doing this on your own machine and you want to run 4 chains in parallel, this MC cores equals 4 will run 4 Markov chains simultaneously on 4 processors on your laptop. If you don't have enough cores on your laptop, you can always reduce that number. And BRMS file refit equals on change. What that does is, I've kind of set this up so that we don't actually have to run the models. They're already pre-fit, so it will load them from a file unless you change the model, since I already have them saved. So that'll just save some time for today. Okay, so we'll, yes, I think you add that options, and we'll add that BRMS file refit equals on change. This may not actually, you may not actually need that on the workspace, but I'll put it there anyway, just for your own edification. Okay. So far, so good. Yes, I see that there's a question in the chat that you cannot find function theme set. Well, you have to make sure that you run all these library calls, otherwise, and that is what loads the theme set among other functions into where you can access them. So if you don't run this line 12, you have to run lines 12 through 17. So highlight them and either click run there or hit Control Enter, and it will run them, and then you have access to all the functions. Okay, good. We're good there. Okay. Okay, so I found this meme and had to use it. So the example data we're going to use are from a maze experiment in the Caribbean. So you've heard of Elf on the Shelf. Now get ready for everyone.
Maze on the Bay.
Yeah,
Maze on the maze.
Thank you. Yes, I had to put that in there, but I did not choose the maze thing just so I could do that. It just was a great and lucky coincidence. Okay, so we're going to read the simulated yield data set. I have this data set loaded in the workspace already. St. Vincent is the island that the data was collected on. If you are not on the cloud server, I also posted the data on a URL, so you can load it from there. But if you are on the cloud server, you can just read it in from this data folder. I have the CSV file there. So hit Control Enter to run that line. And you can see it's got about 300 rows and 7 columns of data. But again, yes, you can uncomment. In R, these hash or pound signs are comments. So if you are not on the cloud server, you would delete the comment mark, and then you could run this line of code. But you don't have to do that if you're doing it on the cloud server, because the data is already there for you. You don't have to load it from the URL, but it would have the same effect. Okay. So let's talk about the data just for a minute, while people get caught up. So this is a picture of the island of St. Vincent. Looks like a paradise. They also grow some corn there, I guess. And this was an experiment that was testing, your basic NPK, nitrogen, phosphorus, and potassium fertilization effects on maize yield. And it was
Hey, Quentin,
yes.
sorry, Melissa Jaw here. I'm a super slow
Go for it.
typer and I don't have two screens, which I wish I did right now. When you
Yes,
get a
someone-
chance,
looks like Amanda or Grant posted the code in the chat, so you can copy and paste it from there.
Okay, perfect. I'm sorry, I'm so
Yeah.
slow.
No worries. Thank you. Please interrupt if you get stuck. Yes, so this experiment was replicated at 9 sites, and it's an incomplete block design. So there's 4 blocks or 4 reps per site, but not all the treatment combinations are represented in each block. So it's an incomplete block design. Very standard, agronomic experiment. And right, because there's untreated controls, there's different levels of N, different levels of P, and different levels of K. So there's lots of treatment combinations, but only some of them are represented in each block. And I sort of simplified an example data set from an R package called AgriDat, which if you ever have to, find some example agronomic data, it is a very good resource because it has hundreds of example data sets, and sort of sample statistical analyses on all of them for different study designs. So it's kind of a nice resource if you're into that. So let's look at the data. I have it on the slide, but let's just look at the data in R. So if you just type in the name of the data set, St. Vincent, if you start typing it and hit tab, it will auto-complete it for you. It'll show you the first few rows. So what are they? Well, there's a site identifier. There's like some code for every site. Every site has a certain number of blocks, which are coded as B1, B2, up to B4. Plot is a numerical ID for the plot. But each plot has a treatment combination of N, P, and K. Fertilizer, I believe, there are 4 levels for each of the 3 treatments: 0, 1, 2, and 3. So unfertilized with nitrogen up to level 3. So we have a lot of treatment combinations, 4 by 4 by 4. So 64 combinations. Only some of them are represented in each block. And then the only response variable we have is yield. I think it's like it might be in bushels per acre. I'm not sure what unit it is, but you can look it up in the help documentation for the AgriDat package. It's called Caribbean Maize in there. And so it's a very simple data set. Hopefully this shouldn't present too much problems in understanding. We're trying to just do some very simple data so we can focus on the Bayesian side of stuff. Oh, and another way you can do that is if you use the glimpse function, glimpse St. Vincent, and hit Control Enter there, it will give you another nice way of looking at it, just in more horizontal, in case that is an easier way for you to look at it. So yes, those are the variables. Okay, so let's just explore the data a bit by making some plots. This class is not about how to make plots in R, so I just gave you the code to make the plots. You can either run it or just look at my plots, either way. We're gonna do some box plots of yield. We're just gonna ignore phosphorus and potassium right now and just look at yield and nitrogen relationship using box plots. So we're gonna do that real quick. I left out something from the slides. We're going to need to convert before we do anything else, a nice thing to do is to convert all the variables that are not our response variables to the factor class, and that will help with the modeling later. So we use this line 34 here. It might be a different line for you by now, but we use the mutate function, which means to change columns using a function, and across means we're going to apply this to many columns. We're going to apply it to the site, block, plot, NP, and K columns, all of them. We're going to use the factor function to convert all of those columns to factor columns. And so if we hit Control Enter, and then if we run the glimpse St. Vincent again, if you hit the up arrow, it'll go up back through some of your recent lines, and hit that again. You can see everything is now a factor. So it won't accidentally think that plot is a integer and try to add them up or anything. It's all factors. I won't go into the underlying R stuff too much, but factors are usually what is used for discrete variables in a statistical model. Okay, so now let's make the exploratory plot. So if you just hit Control Enter on this line here, it will make the plot of x-axis, the different nitrogen levels, and then a box plot of yield for each one. It'll pop up in your plot tab. So here it is. We've got a lower yield in the unfertilized treatment, and then it's kind of a little bit higher yield as we add nitrogen. Nothing shocking there. And you can see that there is a lot of variability, like there's a lot of overlap in the yield. It's not an incredibly strong effect, but it's clear that adding at least some nitrogen is increasing the yield here. So far, so good? Okay. And let's, we have multi-level data here. That box plot was all the sites lumped together. But if we add this facet line of code to our yield plot that we made, it will make a separate panel for every site. So we can see if this fertilization effect is different depending on what site we're at of our 9 locations around the island where the experiment was done. So if you hit Control Enter on this block of code, it will make that. So here, okay, this is interesting. In some sites, yield is low across the board. Adding nitrogen isn't helping. In other sites, we see a strong effect of nitrogen addition. So any model that we fit should allow for the fertilization effect of nitrogen to vary by site. Otherwise, you're going to be missing some important patterns that are going on in the data. And that's why we would use a multi-level or mixed model, which would allow for the random effect for the fertilization effects to be a random distribution and each site to have a different one. That is what the mixed model will let us do. That's all, basic stuff. That's not, that is not Bayesian or anything else. That's just, basic data exploration and model fitting. But I also made a plot for phosphorus by site. Let's hit Control Enter to run that one as well, and potassium too. You can see phosphorus doesn't seem to be as limiting in this location or on this island because the yield. You can see that sites just have different yields intrinsically. Some have low and some have higher. The effect of adding phosphorus, for the most part, isn't doing much. It's not doing much for the yield. So it doesn't seem like they need additional phosphorus. In some cases, a little bit maybe, but not a strong signal. And potassium, let's look at that as well. Similar situation where we don't see as strong of a trend, certainly not anywhere near as strong as we do for nitrogen at some locations. So that's just the example data, nothing too crazy. Okay, so let's talk about how to fit a mixed model to the data. Well, this is just here for reference. This is how you would fit a mixed model with just random effects. Or it's not a mixed model, this is a random effects only model with the LME4 package. This bit is the model formula. Whoops. And this is the important part we're gonna look at. So in R and in BRMF as well, Y, the dependent or response variable, is on the left side. In this case, it's yield. That is what we are fitting the data to see if the treatments affect yield or if it varies by site. And this tilde or squiggle mark separates the two halves of the model formula. Dependent on the left, that's Y, independent on the right, that's X. Here we're only going to fit, in this fake model, we're only going to fit one fixed effect, the global intercept of yield. That's what we put a 1 for the intercept. And then we add on fixed and random effects. Now, the way you set up a random effect is each random effect in parentheses has a left-hand side and a right-hand side in it, separated by a pipe. The left-hand side is the design side, and the group is the right-hand side. So here, 1 means a random intercept, not a random slope, just a random intercept, and grouped by site. So that means we think that there's an overall average yield, and that there is a different yield for every site, a sort of different baseline yield for every site, but nothing about the treatment yet, just a random. Some sites are just bad for yield. They have a low random intercept. Some sites are just happen to have really high yields for whatever reason. They're very good sites, so they would have a high random intercept. And so that's a random intercept for site. There's also a random intercept for block colon site. That means within every site, we have those 4 blocks, and they can also vary in their yield intrinsically. You know, maybe some will just have like poor drainage in the soil there and have worse yield, or some are, you know, who knows why, but we don't know. That's why it is a random intercept that just accounts for any random variation in the blocks within sites. So every site gets its own intercept, and every combination of block and site gets its own intercept. That's the model formula for a intercepts only random intercepts model. And then we had to put what data set does it come from? What data frame in R do the columns come from that we specify, the yield, site, and block columns? Everyone following? Okay, so we're now going to fit a Bayesian model. Get hyped. Okay, this is it. We're going to use the BRM function. That's what we're going to use every time. Bayesian regression model. That's what we're going to use to fit all these models. It's a function in the BRMS package. You can see that model formula is what we just talked about. It's the same as what it would be if it was not Bayesian model, but we have to add a little bit of extra instructions for the Monte Carlo sampler to know how many samples to do and that kind of thing. So we're just going to do 2 Markov chains right now. We're going to take 200 samples, 200 iterations, using the iter argument to say that, and how many of them are going to be used as warm-up so that we can get rid of the effect of the initial starting values of the chains, and they spend some sampling iterations figuring out the best step sizes for how much they jump between each iteration. So that's the warm-up steps. And this is the default, but I put it in here anyway so you can see the initial values are set to be random for each chain. You could also specify them manually. And I'm going to set a random seed so that we all get the same results when we run this. And you can see I did not specify any priors anywhere in here. So if you don't, BRM will come up with default priors for you to use. Later, we'll look at how to modify that. Yes, I see that people are asking if the code can be put in the chat. Let me show you one more time where you can copy and paste all the code from, so that you can see that. If you go to the SEA stats page right here, usda-re-ars.github.io/SEA stats. If you go to that page, and there's a Bayesian Mixed Models text version of the lesson. You go to that right there. You can and scroll down far enough, you will get to all the code that we're doing now that you can just copy and paste from there. It's all in here. You can see, it all has all the output mixed in, but, yes, here's the code that we're looking at right now. So you can copy and paste it from there. Okay, I will close that, for now. Okay. Let's run that code. So, and I've left a bunch of little, ellipses for you to fill in. So we have our intercept. We want to do a random intercept by site. So we say one pipe site. And we want to do a random intercept by block nested within site. So we replace these dots with block colon site. Say what data set does it come from? That's the data argument. We want to use 2 chains, 200 iterations per chain. And out of those 200, the first 100 are going to be warm-up steps. That will not be in the final posterior samples. Start at random values and with a random seed of 1 so we can reproduce. And we're going to call that fit intercept only. If I hit Control Enter, it will run. Okay, so here's the fun part. Every time you run a model in BRMS, it's compiling it. It's going to translate this R code into stan code, which is C++, and then it will run the model. So for these short models, it takes about a minute to compile and only a second or so to run, but it will, for longer models, the compilation is a small part of it. So now someone is asking how many warm-up steps to put. We will discuss that soon, and I purposefully put a very small number here to show you what happens when you put inadequate warm-up, but we will go over that. Okay, so you see that once it compiled, which took, maybe 30 seconds or so, the model ran in under 1 second. And you see it gives you progress indicators as well. So let's go back to the slides. Now you can use the summary method on a model output to get some basic information on all the parameter estimates. But before we actually look at the parameter estimates, we want to see, did this model converge? Did the Markov chains converge on the correct answer? And there's a diagnostic statistic called R hat that as Markov chains get closer to convergence, that value starts out high and gets closer and closer to 1. When they fully converge, it approaches 1. And we see that if we usually, I would say anything less than 1.01 is close enough to convergence. Okay, I see some more questions in the chat. It looks like, yes, error in match R file. Oh, yes, I think that means you had a typo in when you were setting the options. So I will put in the chat what you should replace that with, or yep. Yes, if you run that code there that I put in the chat, and you should get rid of the error. So just copy and paste that and run it. Okay. Hopefully Grant can help you if you get stuck. So let's use summary and take a look. So he hit Control Enter on that. Okay, so this tells us, I'll go through more of the summary later, but there's basically it gives you a variance parameter or a standard deviation of the random effects, and a intercept parameter, that's the overall intercept, and sort of the sigma, the overall model, the variance of the model residuals. You can see there's an R hat column. Some of them are over 1.1, and it even gives you an angry red warning that says parts of the model have not converged. Some R hats are greater than 1.05. Be careful when analyzing the results. We recommend running more iterations and or setting stronger priors. So that's a very helpful warning. It tells you exactly what to do. Usually if you don't get convergence, either you didn't run the Markov chains for long enough, or the priors. Priors can help you get there faster if you have stronger priors. So you can also look at, there's an R hat function that lets you calculate the R hats for all the model parameters, and then I use max to find the highest one on there. So that's another way to do it. If you don't want to look at the whole summary, max R hat. If you hit Control Enter there. Yes, so the highest one was above sort of 1.05 is pretty good. It's ideal to get all of them below 1.01. So that is not converged. And let's also just look. It's easier also to see what's going on here. If you use the plot function, it will call up some default plots of the Markov chains to show you how they behaved. So let's use the plot function on this model fit to see that. Hit Control Enter. Okay, so here are basically the posterior distributions of some of the most important parameters of the models, which is the intercept, the overall average yield across all treatments and sites, the SD, or the standard deviation of the block effect, random intercept, the standard deviation of the site effect, and sigma, which is like the residuals at the plot level of the model. Now here's what these are called trace plots. Each one of them has 2 lines, which shows the Markov chain as it was going through the 100 samples after warm-up. You can see that the 2 chains are not really on the same value. They kind of go up and down. They are not mixing well. Mixing meaning they have not stabilized on the same solution. They're kind of searching around to find the right answer, but they haven't found it yet. They haven't got to the same answer. So when you see a trace plot like this, that's just additional confirmation that your model has not converged. Any questions?
What's the
Yes.
y-axis for the?
Yes, this is the parameter value. So like it just the yield is around 16 on average. If you just took the average, like if you just took mean of the yield column, it's probably going to be 16-ish. Yeah, so like it's trying to just estimate the overall global average and then have random deviations by site from that. And if your data are balanced, which this more or less is, just taking the plain old average of it is going to be a very similar value to what you get for this intercept. And yeah, and the x-axis are the iterations. We have 100 that we did. And yeah, so this means like the standard deviation by block is about 1. So like blocks vary by about 1 bushel per acre standard deviation. Sites a lot more. It's like 4 to 5 bushels per acre different. Yes, so that's what whenever you run a model, it's great to take a look at those diagnostic plots. It can help you make sure you're getting the right answer. So I would recommend always doing that. Okay, so the warning message said either increase iterations or set stronger priors. Well, the easiest thing to do here is just to add more iterations. So let's do that. We'll do 1,000 warm up and 1,000 sampling instead of 100 and 100. That's 2,000 total. And you can actually use the update function, which if you don't want to recompile a new model, but just draw more samples, you can use the update function to do that. It lets you draw more samples without recompiling the code. So you want to do update, still with 2 chains, but now 2,000 total, 1,000 warm up instead of 200 and 100. So let's do that. So we're going to use update here. And scroll over. Okay, we want 2,000 total per chain. Yeah, so this iteration is always per chain. It's however many chains you do, they'll all do 2,000 iterations, and 1,000 of them will be warm up. So 1,000 warm up, 1,000 sampling. Okay, let's hit Control Enter and run that. So you see does it real quick this time because we didn't have to compile the model, it just sampled it in a second or two. Now, if we, what I have us here, what do I have to do here? If we do the plot, look at the trace plots again. Do plot, control enter. Okay, now this is the business right here. This is what you want to see. In the lingo, they call this the hairy caterpillar. That's exactly what you want to see because it the two chains are right on top of each other. They are not, you know, the chain one, the darker line, the chain two, the lighter line are right on top of each other. You can't perceive any trend up or down as you go from 0 to 1,000. They're just going back and forth, because they found the right answer and are just sampling around that. And they're mixing. They have both hit the same spot. You don't see them stabilizing in two different locations. So it's like, that's great. This is an hairy caterpillar, meaning that there's no autocorrelation. It just goes up and down. So it kind of looks like a fuzzy caterpillar because each point is not, each sample has no real correlation with the one before it. That is a dead giveaway that your model has converged. So that's great. That's what you want to see. Hairy caterpillars are good. I see there's some questions in the chat here. What's going on? Oops. Somebody asked if you can only run one chain. And so we mentioned this before, but it is, you should always do at least two, optimally, 4 or more, because you would not be able to know if the answer that it came up with was actually the true optimal parameter value, because it's sampling the probability distribution, trying to find where the highest likelihood is. It's possible in a multidimensional integral to get a local maximum, to be stuck on a local peak when the real peak is somewhere else. The more chains you have, the less likely it is that all of them found the wrong answer independently. So you want to do more than one. But once you're sure it's converged, you can combine all the samples from all the chains together if you know they've all got to the right answer. So let's look at the summary function for this and take a look at what hit control enter. Now we can see all the R hats are, close enough to 1, so we're happy it converged. I mean, really, it was pretty close before because the intercept is still around 16, just like we got when we calculated the mean of the data. And another thing you can see is that it gives you the lower and upper 95% credible interval of it. So that is, I'll tell you what that is in a minute, but it's kind of an estimate of the uncertainty. It goes from about 13 to 19. So we think that there's a 95% probability that the true overall average is between 13 and 19, and kind of the median of that is right around 16, which is good. That's what we would expect because it's what the data already say. And the block standard deviation is about 1, and the site is closer to 5. There, you also get a credible interval on that. So that just indicates that more random variation exists between the sites, not as much between blocks within a site, which makes sense because their blocks and within a site are closer together and should be more similar. And there's also the model residuals. The standard deviation of plots is 4. So there's actually a lot of variation among the plots too. So that's kind of going to make it harder for us to pull out a signal. Okay, so we're having some more questions about what warm-up is. Now, the way that the Hamiltonian Monte Carlo algorithm works is the algorithm has to spend some time taking kind of trial samples from the posterior to figure out the optimal kind of tuning parameters it should use for sampling the distribution. So it takes some samples to do that, but those should not be used in your final estimate of the answer because they're not good samples of the posterior. They're just, it's trying to find the best way to sample it. So we need to always set aside some iterations for warm up and to get rid of the influence of whatever initial random starting values we chose. And And we also have a question about setting stronger priors. We will get to that soon, so I'll address that when we come to it. Okay, so. Thank you for the questions, though. Now, I just want to make a note of the terminology. In the summary, it says group level effects and population level effects. It doesn't say fixed and random. Usually, so group level effects is what most people call random effects, and population level effects is what most people call fixed effects. So like, you know, you're making inference of the entire population on the fixed effects, but some Bayesian people say, well, everything in Bayesian analysis are random variables, so it doesn't make sense to say fixed and random. So that's why they're calling it group and population, but just to like reduce confusion, I'm gonna call it fixed and random in this lesson, even though if you look, it's calling it group level effects for where we would typically think of that as random effects. Population level is kind of just think of that as a synonym of fixed effect. Yeah. So that's hopefully not too confusing. Okay. So let's see. Yes, group meaning random, population meaning fixed. Okay, so I just mentioned this already, but there's on the parameter summaries that 95% CI. Usually you would say, well, that's confidence interval. Yes and no, it's similar in interpretation, but in Bayesian terminology, it's called a credible interval. It just means we're 95% sure the parameter's value is in the 95% credible interval. And that's based on basically taking quantiles of the posterior distribution. So like it would be if you took 2.5% off here and 2.5% off there, you got 95% left in the middle. That's the 95% credible interval of the intercept, which was around 13 to 19. So like 13 up to 19, 95% of the distribution samples are inside of that range. So our posterior probability that the intercept is between 13 and 19 after we fit the data, the models of the data is between 12.8 and 19.3. That's credible interval. And I wanted to also show you don't have to use 95 as the credible interval. You could use any number that you want to. 95 is kind of based on that traditional cutoff of P is less than or equal to 0.05. But if we're not doing kind of null hypothesis testing, we are not necessarily limited to using 95. So I just want to illustrate, you do not have to do that. I just want to you don't really have to do this in practice, but I'm trying to just illustrate how the credible intervals are calculated. So this code here, as draws DF, will take all the posterior samples for all the parameters in a model and put it into a data frame. And then we're going to take the median and the 5 and 95 quantiles. So if we took the 5 and 95 quantiles, what % credible interval will that give us? Does anyone want to take a stab at that?
Dr. Reed, there's a request to make your cursor larger if you can.
Oh, yeah, let's see. How do you do that?
Are you in PowerPoint?
I'm not sure how to do that.
Okay, we can look at it at the break.
Yes, in the break, I'll try to do that. We'll do maybe in around 11, in about 20 minutes, we'll take another break. So yeah, let's show manually how to do the credible interval just for illustration. So as underscore draws underscore DF, we'll take all the posterior draws and turn them into a data frame or like a big matrix. We're calling it post samples. So you see there's 2,000 observations of 54 variables. 2,000 because we had 2 chains that each ran for 1,000 post warm-up. We have 2,000 samples. We're combining all the chains together. And 54 variables because if you look at it, we have our intercept, the variance of the random effects, but the way random effects work is that every block and every site has its own intercept. So like there's a lot of parameters in that model. There's 54 parameters because we had there's like 4 blocks at each of 9 sites. So each site has its own intercept, each block has its own intercept. Then there's like some extra parameters. So like we end up with around 50 parameters, which means we were sampling like a 50 some dimensional integral when we were doing that. Like that's, and this is a very simple model. So that shows you how quickly the dimensions will blow up. So then there's a column called B underscore intercept in BRMS. All the fixed effects begin with B, like beta usually they call them beta. So they all begin with B. So that just helps you know which ones are the fixed effects. And so we want to just pull out that one column of it, B intercept. And if you hit Control Enter, so now we have a 2,000 samples of our intercept. You can see it's like 16, 15, 16. It's all around, those are all samples from the distribution of what we think the intercept is based on our knowledge and the data. And so if we take the median of that vector, that's our estimate of the intercept. So it's 16.05, which is, I think this might give you the mean and not the median. We can do the mean as well. You want to do the mean too? Yeah, so 16.08. So this is actually giving you the mean and not the median, but you can see they're very, very close to one another because it's symmetrical. And if we use the quantile, oh yeah, so I was asking before, if we take the 5 and 95 quantile, what credible interval will that give us? Does anyone want to know what the answer is there? If the 95% interval goes from 2.5% to 97.5%, what is it if you go from 5 to 95? We're taking 5% off one side and 5% off the other side.
90.
That's right. If we start with 100, we're taking off 5% from each side. That's giving us the middle 90%. So this will give us, yeah, it's just a different interval. It goes from, there's a 90% probability that the intercept is between 13.5 and 18.7. That's a bit narrower than the 95% interval because it's a lower probability. So we're taking off a little bit more from each side. That's just to show you can calculate it manually for any percent you want, not just 95. And the nice thing about the Bayesian models is every single value or quantity you can calculate has a posterior distribution. So anything, you can calculate uncertainty on anything. In a frequentist model, that's very hard to do, especially for random effects. It's kind of hard to get confidence intervals on random effects in your model without doing bootstrapping and stuff. But in a Bayesian model, you can just do it just like you would with anything, because everything in a Bayesian model has a distribution. You can just pull that out. Oh, somebody said they got a different value for the median. Some people, yeah, I think that if you are running this on a different system or the random seed got initialized differently, you might get a slightly different result. Since we're only doing a small number of samples, if you did a lot more, they would converge to a much closer value. So some people got 15.99 instead of 16.03 or something, and that's a function of a different random seed, and you'd want to run it for more iterations to get rid of that noise. But it shouldn't affect the inference because it's very close. Another thing you might want to do, this can be done in not just Bayesian, but I want to show it as well here. The variance decomposition, we might want to look at how much proportion of variation is at each of our levels in the data. ICC is how you would do that in a mixed model. Again, not just for Bayesian, but for any mixed model, you can do an ICC called intra-class correlation coefficient. And that's basically like getting the variance components for each of the levels, each of the random effects. Yes, I didn't, yes, you might have to add a random seed to update. That's true. You probably would need to do that to get the same answer. We could test that out later. So if we do ICC, intra-class correlation coefficient, and we want to set by underscore group, equals true, so it'll give it to us for each random effect level instead of just overall. Control Enter and run that. You can see that this kind of fits what we're showing, that blocks are only explaining about 3% of the variation. Sites explain about 60% of the variation. And again, we've ignored treatment here, so this is just treating everything as random. So that fits with our looking that the standard deviation of blocks was around 1, the standard deviation of sites was a lot bigger. So that makes sense. So block is not as important to account for in the model. Site is very important to account for because it's explaining 60% of the variation. So far, so good. Okay, let's do a little bit more before taking a break. Now, yes, I just put a slide here that says we do need this multi-level model, at least for site, because the variation explained by site is very high. So if we ignored that and tried to fit a model just looking at the treatment effect, ignoring site, we wouldn't get kind of an accurate result. And but even though block has a very low effect, I would recommend including it anyway. If that's the way your study was designed, I would recommend including it anyway, because the model should correspond to the study design. And a nice perk of the Bayesian approach is that even if in a frequentist approach, if the values were close to 0, if there wasn't much variation at the block level, your model would have trouble fitting, but the Bayesian can still pull out those estimates even if the block effect isn't very big. So that's kind of a nice perk. So I would recommend including them if that's the way you designed your study. Okay, so that's kind of just we're building this up little by little. We've only looked at the mean of yield and random variation by site and block. We haven't looked at any treatments and see if they influence yield. Well, let's add a fixed effect to the model, the fixed effect of n. We're just going to do n for now. We're going to ignore p and k for a bit still. We're building it up little by little. Yes, that's I believe I changed the factors when I changed the example data, so ignore that part of the slide. We're just going to add n plus n to the to our model formula here to add the fixed effect of nitrogen. And now we're going to do 4 chains as I recommended. That is a good one, a good number to use. And still 1,000 warm up and 1,000 post iterations. And I also, oh, by the way, and a different random seed. If you're running this on the server, I've pre-saved the results of this model, so it won't have to compile and run. From now on today, if you're running it on the server, you will not have to actually sit there and wait for the model to sample unless you want to play with it on your own and change the model around. It should, hopefully, cross fingers, if everything works as it intended, this pre-saved model will be there for you and you will not have to, sit there and wait, because that's nice for learning purposes. So you can see I used the yield is still our response variable, tilde for the formula to separate the independent and dependent, 1 because we still want an intercept. Actually, if you excluded the 1, it would fit an intercept by default, but I'm including it anyway here explicitly just to make it clear we're doing an intercept. And n is the name of the column that is the fixed effect of n treatment. I've included everything else. The data are still the same, 4 chains, 1,000 warm up and 1,000 post warm up. The random seed, it can be any number you want. I just put 2. And the file, you can see in the rest of the model fits we're going to do are all saved here already. If you run brms and this file didn't exist, it would create it. If it already does exist and you haven't changed the model, it will just load it off of that file. So I'm gonna run that and hopefully, yep, so it didn't do any compiling or running, it just quickly loaded the file that already was there. So we didn't have to, which is nice if you're doing the same analysis. If you're just going back in, quit R for the day and come back, you don't have to rerun the model. Some of them take hours, so that's kind of nice. We're still using the default priors, by the way. I'll show you in a minute how to modify that. So as I said, we've used 4 Markov chains, which is good practice. I used 2 in the example first, but we can be more confident of our answer if we have all 4 that converge. It looks like we have some troubleshooting things in the chat. Object yield not found. Yes, that would be because there's no object in our overall workspace called yield. It's a column in the St. Vincent data frame. So you have to make sure that it's finding that by making sure that data equals St. Vincent. Okay, let's look at a summary of this. Now you can see we have the same, it tells you, how many draws there were and stuff. We still have our standard deviation by block and by site. They're about the same as they always were. Now we have a new estimate for the intercept, and we have 3 slopes, 3 treatment effects, because there's 4 levels of nitrogen, the control, low, medium, and high, which is 1, 2, and 3. So it gives us the intercept is now 13, and the difference between each one and the intercept is our population level effect. You can see we have credible intervals on that. They are all well above 0. So like there's a 95% probability that the effect of adding low nitrogen is between 2 and 4 benefit to yield relative to having no nitrogen at all added in the control. And you can also see our residuals are 3.5. Before, I think they were a little bit higher, but were they? Yeah, it was 3.9. So since we've added some treatments to explain some of the variation, the residuals of the model are less because we've taken up some of that variation with the treatments. Not a lot. There's still a lot of random variation because it's a very noisy data set, which, as you know, in real life, a lot of these data sets are very noisy. So no surprise there. Yes, if we look, and also you can see the R hats on all the parameters are less than 1.01. So we think they converge. But you should always plot to take a look at the trace plots. And that'll help us see what's going on. And now it says hit return to see next plot because there are more than will fit on one panel. So we see, okay, here's nice hairy caterpillar, looking good. If you hit enter, it will show the rest of the parameters. So there's a couple more, the standard deviation. They all look like hairy caterpillars. And you can see this one is a little bit skewed, the standard deviation, because standard deviation cannot be below 0. So you have a more skewed distribution, but it still looks like a hairy cat. It can't go below 0, but it still has a hairy caterpillar. So like the BRMS automatically constrains it so that standard deviation cannot be negative. It has to be 0 or greater. So yes, what should we look out for when looking at these plots? Again, you want to see that all the chains are on top of each other, that they are mixing well, they have converged on what we think is the correct solution, and that there is no trend going up or down. Like if you would draw a line through that, it'd be more or less flat. It's not going up and it's not going down. It's stable. That means that it's converged. So that is the diagnostic that you want to look at. Does that help? Okay, so we also now want to think about the priors a little bit because I've kind of told you at the beginning how important were priors, but we've kind of been just accepting that the default prior was good to use. But if you use the function prior summary, it will tell you all the priors that were set by default on the parameters of the model. So let's look at that prior underscore summary of this thing we call fit underscore fixed nitrogen. Hit control enter to run that. Okay, so here's what we got. We have flat priors which is like a uniform distribution, basically was fit to all the fixed effects. Each of the three slopes were set as a flat prior. The intercept is set as a t distribution with the mean of it being the mean of the data. And all the standard deviation parameters are set as t distributions, which have you see this LB column, they have a lower bound of 0, meaning they cannot be negative because standard deviations can't be negative. So it's kind of like a half bell curve, basically, distribution set on them. These, usually I do not mess with these priors. These are very sensible defaults. It allows, the standard deviation of them is set based on the data. So I would not recommend, unless you're a very advanced user, tinkering with the priors on the standard deviations. BRMS sets very good defaults for them. So don't play with those unless you kind of have a very good reason to. But okay, here's something that you do often have to edit. It will give you flat priors on all the fixed effects. What a flat prior means is it's completely uniform. We have no prior beliefs that any one value is more likely than another for the slope, the difference between control and low, control and medium, and control and high. Yeah, you can say, okay, well, we're not being subjective, like we're being Vulcans, we want to say there's no, we have no emotion, we know nothing coming into this, but is that really what you want? Well, maybe not, because you've actually assigned just as high of a prior probability to completely unrealistic values that could not even be possible given the data. Like the yield only, if you look at the range of the yield in the data, if you look at range of the St. Vincent yield column, it only goes from 3 to 30. So like those coefficients of the difference between treatments is not going to be any more than, it definitely can't be any more than 30, right? Because that's like the highest value we even have. But this flat prior is saying the slope could be 100, it could be 1,000, it could be negative 1 million. There's no prior probability assigned to any one of those values as any higher than the other. It worked out in this case because we had such a strong signal in the data that it was able to find the correct answer without having any help from constraining the priors to reasonable values. But we kind of do want to give it a little bit, oftentimes you will not get convergence if you just ignore that and go with the flat priors. So I want to show you how you would do that and why it can be helpful. So let's take a look at that. Yes, so I should have put the slide up because I just said all that stuff. It was okay that it converged, but let's constrain the prior to reasonable values and try again. So let's try normal distribution with a mean of 0 and a standard deviation of 10. That's kind of a good choice because it's centered at 0. So like it's a bell curve centered at 0. We think having a positive effect is just as likely as negative, which might not even be reasonable in this case because we probably think that adding nitrogen is not going to make the yield less, but it's fairly conservative anyway. And standard deviation of 10 means we're still assigning a pretty high prior probability to extremely large effect sizes, since the very highest yielding plot was only different by 3 to 30 bushels per acre. So having an effect size of 10 is huge, right? I mean, that's like a giant effect of yield, of fertilization on yield. So we're being very conservative. We are still assigning a high probability to large effect sizes. We're being still pretty agnostic and saying we're going to let the data decide what the effect is, but to help the model converge, we're going to keep it within a reasonable bounds to something that's not just flat out impossible given the data. Now we use the prior argument in BRM to do this, and there's a function called prior that will assign a prior to each class of parameters. And so we're going to use normal of mean 0, standard deviation 10. And class equals B, as I mentioned before, fixed effects in BRMS are always called B, which stands for beta, which is kind of like the standard notation for fixed effects. So B is what you put for the fixed effects. Kind of annoying they don't just say fixed effects, but you have to just know that it's B. So let's put that in. Now, yeah, everything else is the same. I put a pre-fit model in the directory, which is called fit of fixed n with priors. And so we just use the prior arguments to this, and the function is also called prior. And the normal distribution, mean of 0, standard deviation of 10, and B for the fixed effects. That's what you should enter in there. Everything else is good to go. Control enter to run it. Because the model was already pre-saved, it didn't have to compile and sample, it already just loaded it for me. And yes, let's look at the summary of that to see how it affected the fixed effects. So on this line, I have that typed in for you. Okay, you can see, okay, before we had here, now the mean estimate of the effect of adding low nitrogen is 3.38 with a credible interval from 2.38 to 4.39. What was it before? It was 3.43, ranging from 2.41 to 4.45. So that's like very close. We didn't really change our estimate that much, but they did all go down a tiny bit, 3.4, 3.9, and 5.0. Now it's 3.38, 3.9, and 4.9. So they actually did, the prior had a tiny effect. It changed our estimate by kind of a minuscule. Now, I mean, it changed it by 0.1, and the credible interval is, 2 or 3. So it's not a big effect. It won't really affect our inference, but it did make a difference. And in some cases, it can make a big difference. Otherwise, there wouldn't be a point in having them. And that's why it is critical when you are reporting a Bayesian analysis in the literature, you should always be explicit as possible about what priors you use. And if possible, have a justification for why you use them, because it is an important part of the analysis. And that's very important. And, if you really want to do a good job with it, and then you should run a model with a range of priors. You could do a sensitivity analysis showing how much the choice of prior affects your results. That's something that you could also report if you want to be really cover all your bases and be very conservative about it. Yes, so let's, so somebody asked a question in the chat. I am still unclear about a flat distribution. Could you explain how to understand that the prior distribution is flat, given that these are factorial priors instead of continuous variables and vice versa? Okay, so these, if you look at it, the parameters that we are estimating are coefficients of a regression model where we're looking at the intercept is the control level, and there's 3 discrete factors. So you're right, the treatment is a discrete variable, but the coefficient is a continuous variable. So the effect of adding low nitrogen on yield is a continuous variable. Like it could increase yield by 3, it could increase it by 0.01, it could decrease it by -5. It's a continuous variable that could, in theory, take any value. So our prior distributions have to reflect that, and our continuous distributions. So the flat prior was uniform. Now in our new model, we've used normal distribution of 0 and 10. And the other question is, what was the basis of choosing 0 and 10? Well, again, I choose 0 because typically that is seen as, it's kind of like the Bayesian version of a null hypothesis. We've put the highest probability on 0. That's a null effect. So you can think of it as a null hypothesis because we're saying there's 50% probability of being, prior probability of being positive, 50% prior probability of being negative because it's centered on 0. So that's like a null hypothesis. So that's my rationale for choosing 0 as the mean. Now the standard deviation of 10, that's a little bit more subjective. And I picked it because it's kind of in the middle, in kind of the order of magnitude of the data. The data range from 3 to 30. So 10 is kind of like in the middle of that order of magnitude. I wouldn't want it to be 100. I wouldn't want it to be 0.01 because that would be a very, very tiny effect. If I put 0.01, it would assign a very, very low prior probability to nitrogen affecting yield at all. Here, let's actually do that just so we can see. Let's say I put it 0.001 as the, you all don't have to do this with me, but I will change it to 0.001 and run it again and see, since we've really tightened up the prior to something ridiculous, let's see what we get. So this will have to compile since I changed the model up a bit. But let's take a look. But thank you. I really appreciate all the questions. It does help everyone's understanding to kind of interrogate these assumptions that we're making and stuff. Yep, so let's see, give it a minute to run. So you can see it's just hopefully takes a few seconds. Okay, now if we look at the summary of that new model. Yeah, so, well, I kind of did it, I probably went too far. You can see it's assigned 0. The estimate of every parameter is 0 and the credible interval is just tiny. So yeah, I probably went too far. I should have just done 0.01 or something to give a better example. But because we've said, okay, I have a very, very, very strong prior belief that nitrogen does not affect yield, I'm going to put that knowledge into my model. The data are trying so hard to move the needle, but they can't because the prior probability is so low to have a big effect that the data cannot change our prior beliefs. So yeah, so that would be a bad prior to put because it's not allowing the data to speak for themselves at all. It's kind of just like, that would be like a prior you put if you, of like the 50% coin flip, you would need to have like a really big data set with a very strong effect to change your belief. Or like if it was like somebody who claimed they were psychic or something, you believe a priori that that's not possible. You would put a strong prior on a 0 effect of psychic powers or something. Okay, so I got a couple more questions in the chat. After these questions, I think we can take another 10-minute break. So I'll answer them and then we'll go to break. So Xiang Li asks, are all independent variables are categorical in this example? What if you have continuous variables as your independent variables? Is it still similar codes? Yes, the syntax is exactly the same. You might have to think about what priors to put. Actually, that's a great point because if you have a lot of times if you're doing a multiple regression with different continuous predictors, you will want to, this is the case for Bayesian and not, you'd want to standardize or scale your predictors by Z-transforming them before you fit the model so they're all on the same scale. That's especially important for the priors because like if one of your variables was, you know, some like concentration that's 0.00001 and the other is temperature that's 50 or whatever, then they're going to have very different slopes. But if you standardize them, the priors will be in the same range and you can use the same order of magnitude prior for everything. But other than that, it will not change the code at all. So thanks for that question. And can we create loops to test multiple priors? Sure, yes, there's no reason why you couldn't wrap this thing in a loop and have like, instead of put a variable here and then test different priors. I won't, do that right now, but you could, and that would be a great idea. What should we do if one of the priors generates a binomial distribution of the outcome? So do you mean like if the posterior had two humps in it or something like that? That would probably indicate bad convergence, and I would tweak the priors and try to add more samples to get rid of that, because that is very unlikely to, that would probably just be a sign of bad performance of the Markov chains. And is there a reasonable starting point to the numbers of iterations, chains, and warm-up? Well, the default actually is to have 2,000. I just set all these values here, but this is actually the default by BRMS: 4 chains, 2,000 iteration, and 1,000 warm-up. That's the default. If you never, it would actually work in most cases, because the HMC algorithm is fast enough to get you the right answer for most models within a couple of thousand. Sometimes I have to go up higher. I hardly ever have to go above 10,000. That would kind of be like the most I would do in a practical circumstance. And yeah, just keep trying until you see hairy caterpillars. That is exactly what you had to do. And then we have another question about what we're looking at in the trace plots. Again, we want to see the hairy caterpillars. We want to see no trend up or down, means it converged, because it's not still trying to find the right answer. It found it and it's just going back and forth around it. And all the chains are right on top of each other. It doesn't look like, if I can go back through my plots to the one that was bad, let's see. Yeah, here's the one that's bad. You can see, sometimes you can see it's clearly going down for a while, then it goes up for a while, that's bad. And the chains are not overlapping. They are often on different values. That is bad. And if you see that, you're going to want to add more iterations. Okay, so let's see, it's 11:12 Eastern right now. Oh, there's one more question. What would be an example of a situation requiring 10,000? Would it be a case of very small effect? Yeah, usually, yes. If you have very small effects, usually it's harder to characterize that distribution, so you might need more samples. And yeah, or if you just have a very complicated random effect structure, like repeated measures, covariance and time series, or like spatial dependence, that kind of stuff. Those are just more complicated models to sample, and there's covariance is always a problem, because there's like dependence between the parameters, and that's where you need more samples for, basically. If you're really trying to get, like, to get the mean of a distribution, you don't need that many samples, but to get the tails, since there's just not as many out here, you need more samples to characterize the tails of a distribution than you do. You know, a couple hundred is plenty to more or less get the mean or the median. But if you really want to know some very high, like if you wanted like a 99 credible interval, you can't really just do 1,000. You'd have to do more than that. Thanks again for the questions. Let's break for 15 minutes and start up again at 11:28 Eastern, 10:28 Central. And I'll be here. I'll just hang out here and answer any more questions that come up, but folks can take a break for 15 minutes.
You know, try to do the mouse.
Oh, yeah. Did you figure that out?
Yeah, just in the settings in the bottom. Just have the mouse.
Oh, yes. Yeah, thanks.
They get
Okay, hello, everyone. I see that we have a couple of questions in the chat, so let me just address those before. Looks like there's some great discussion here. Lena asks when you would want to use Bayesian versus mixed linear model. Well, this is also a mixed linear model, so whether it's Bayes or not, a mixed linear model is appropriate. It's just what method are you using to estimate the parameters? Is it maximum likelihood, what you're used to, or is it Bayes? Well, for these simple models, it really doesn't matter. Like, you're gonna get a very similar answer either way. So, but it's good to have the Bayesian approach in your toolbox for those cases where where you have GLMMs with weird response distributions, you have a lot of weird covariance in space or time. It can work a lot better. Yes, and but we can talk more about that later, I think, too. And then there's another question: if there's a continuous variable instead of categorical, and then there's two optima for yield, making it a binomial distribution. Okay, yes, if you truly have a continuous variable with two optima for yield, then a linear model will not be appropriate, right? Because it's not a linear function of that variable. So priors are not going to help you. No matter what you do to the priors, it's not going to be the right model. So it won't matter how the priors are. What you're going to do is fit a different model. You're either going to have to discretize that continuous variable into bins to accommodate for those different peaks, or you're going to have to put in some non-linear function with respect to that variable. Yeah, like quadratic or whatever. That's what you'll have to do. Priors will not help you. Yes, and could you assign a binomial or some other distribution to prior data? Yes, you could for sure, and that is exactly what. Yeah, they don't have to be normal distributions. Any distribution can be used for prior data. Like the T distributions that are being used for the standard deviations and stuff. I won't get into all those possible situations here because this is just the very intro, but yeah, that's sort of a more advanced topic. Can you use categorical data instead of continuous data for a predictor variable? Yes, of course you could. Here we are using categorical, and yeah, it would work the same either way. So. And oh, there's also a question if the recording will be accessible after. Yes, it will. At the end, after this class, I'm gonna send out a follow-up email, and I have all my previous recordings, or at least of the classes that I've managed to record, are on the SEA statistic workshop page on Axon. It just got moved over to the new Axon Plus thing that y'all might have seen. So they're all on there, and I'm gonna post this one on there too. Yep. Okay, so thanks for all the questions. I'm going to, in the interest of time, try to get back started here. So I'm putting screen share back on. I got some tips on how to make a really badass mouse that's huge and yellow. So now everybody should be able to see that. Yes, hopefully you can all see that now. Okay, so where we stopped was we just did a model with priors, and there's more model diagnostics than just looking at the trace plots. We also want to know how well the model fits the data and if it's appropriate model. Just like in your frequentist models where you look at, QQ plots of residuals and stuff like that, we still have to make sure there's no exception here, that we want to do an appropriate model for the data. So PP check is a very good one, very good diagnostic plot to look at in Bayesian models. That stands for posterior predictive check. And what that does is it makes kind of a histogram or a density function of the data. Then it takes some random draws from the parameters and predicts the fitted values. And you can see if the data have the same distribution as the predicted values, and that means the model is fitting the data well. So let's take a look. Let me close that there. Let's take a look at I went to sleep while I was gone. Wow, this mouse is almost too big, but I think it'll still work. Okay, somebody says the mouse is still tiny in Zoom. Well, oh, that's too bad. So I don't know how to edit it in Zoom. I apologize. But trust me, if you're here in Raleigh, it's huge and yellow. Okay, sorry about that. Sorry, I'm not, okay, well, anyway. All right, where were we? It looks like we are at the, we're gonna do the PP check on that. Yeah, the mouse is too big. I can barely like figure out where to put it. Okay, PP underscore check. And now that will give us a, hit control enter. Okay, so it's a density overlay. So this black line here is the data. And the thin blue lines are the 10 draws, the data predicted from 10 draws of the posterior distributions. So you can see, you know, more or less the residuals match up with the data. There's the blue lines are kind of on top of the blue line, but there's kind of these two humps in the data that are not really captured by our residuals, or our fitted values all are kind of just like bell curves that are symmetrical. The data have two humps. That might, I think it's because we left out the phosphorus and the potassium predictors. So hopefully once we add those, we should see a closer fit, but also it could just be a little noise in the data and you don't want to necessarily overfit. So at least the shape of the, you know, we don't see like some weird skewed thing in the data that's not present in the fitted values. They're more or less centered on the same point. So like that's decent. That's decent. Okay, so we saw the median and the mean and 95% credible interval of all the parameter estimates, but we can get the full uncertainty distribution out all the posterior samples to make tables and plots that show the full distribution, not just 95%. And Tidy Bayes package is a great one that has a lot of functions for pulling out data from the or posterior samples from BRMS fits, and you can and make plots with them. So we're going to do that to make some plots. This is kind of more manual than you would normally do it, but I'm just trying to show you how it works. Gather draws is another way to make a data frame from posterior samples, but instead of doing the entire every random effect, it lets you pick specific ones. So we're going to gather draws from this model that we fit, the intercept and the three slopes. That's just what they're called in the model. You can use a function called, I believe, get variables to see what the names of all the parameters are. So yes, if I do, I'll just show you that. If you do get variables, it fixed n with priors, it'll tell you what all the parameters are. You can see there's all the random effects, the R side random effects are in there as separate parameters, but the ones that are important are the intercept, beta, so the fixed effect of nitrogen, and the level is 1n. The names of the three treatments were 1n, 2n, and 3n. So it's nitrogen is the variable and the level is 1n, so it's n1n. So we want to do gather underscore draws, and we want to do the intercept and the b underscore n1n, b underscore n2n, and b underscore n3n. We want to get all those. Hit control enter, and then you can use a function called median and quantile interval, QI, which will give you the median and quantiles of the parameters. And you can do as many levels as you want. Like you can do a 66. Sometimes I like to show 66 and 95 because 66 in normal distribution is about 1 standard deviation. 95 is about 2 standard deviations. So that that allows you to characterize it well, and you know, you might want to do 99. This is just an example. So we use the posterior slopes and we get the median underscore QI. You can see, it gives you, oh, you know what, this is from when I accidentally overwrote the model with this normal of 0.001. So these will look very different than what you will get. Let me just run it again with 10 again, as you all have, since unless you did run it as the, oh, so you said I have to do that again. Okay, because it went to sleep. So I'll have to set that path again. Do that. That's only a thing that happens on this cloud server. You wouldn't have to deal with that if you're doing it on your own. That's just a function of us working off this server. So I'm redoing that so that we can get the same results again. And everybody, it should all look the same. I see somebody else change the prior to 0.01 as well, and so then you get the slopes all like pretty much got estimated as 0. Okay, so let's yeah, sometimes if I go off script, things change from what is expected, so good thing we caught that. So let's see, I'll get the slopes again, find the medians and quantile intervals. You can see, yeah, the 66% interval is a bit narrower on the intercept. It goes from 11 to 14-ish. The 99% interval is very wide because the higher the probability we want to accommodate, the wider it will be. Goes from 8 to 17. So that just shows you can do as many intervals as you want. And okay, let's see, right. Well, we'll just skip that. Actually, that's not that informative. Let's go straight to the estimated marginal mean. So if you were in this workshop last year, we did this for the frequentist models, but EM means, the estimated marginal means package, can be used to get means for Bayesian models as well. It's like the LS mean statement in SAS, like the Bayesian procedure for mixed model fitting in SAS also has an LS mean statement. It's exactly just like it would be if you were doing it in frequentist. You want to, yeah, what you often want, no matter how you fit the model, is you want to get predictions in each of your treatment levels. So like, we don't just want to know the difference between each one and the control. We want to know what is the prediction of yield in an average site and an average block for every treatment. Like if you took a random spot on St. Vincent Island and put fertilizer on, what would our prediction of the average yield be? And in the Bayesian model, it estimates that for every draw from the posterior distribution, and then you get a posterior distribution for those means as well. And you can do credible intervals on them, just like you do for the parameters. That's how you estimate uncertainty in them. So, oh yeah, I guess I did do that. Okay, yes. You can do it by hand, which is basically adding the intercept to the slope for each treatment to get the difference. So we have the intercept is the mean of the control, and the slope for low nitrogen is the difference between low nitrogen and the control. If we add the control to the effect of low nitrogen, we'll get the mean for low nitrogen. So there's like a kind of, you would have to do that in a very cumbersome way by reshaping the data, manually adding it together, and calculate the mean and quantile interval. So yeah, the way I've given you most of that code, except for you create the mean for one nitrogen by adding that data intercept, it's a capital I. Again, yes, you wouldn't normally have to do this, but I'm just showing you how it works. Yes, so that's, yeah, plus beta B underscore N1N. That's the posterior mean just for the one nitrogen, the low nitrogen. And then we get the median of that and quantile interval. It'll give you the 95 by default. So yeah, so the average prediction for adding low nitrogen is to have a yield of 16 bushels per acre with a 95 credible interval of 13 through 19. That's how you do it by hand. How would you do it? This EM means function from the EM means package works with all kinds of different models from R, including the BRM models. And basically, the first argument is the model fit that you want to get the means for. And the second argument is get means for which treatment combinations you want. And it's a one-sided formula, so it starts with a tilde and then has the factor or factors that you want the means for after that. We're just doing it by nitrogen right now. So we want the EM means of the fixed N model fit. I guess that's the one that had the default priors, but it shouldn't matter. And we want it by nitrogen. So tilde N. Hit Control Enter. Okay, and if you just type that N underscore EM means into your terminal, you'll see the means. So yeah, it's just like we would have thought. The intercept mean is 13, and there's the lower and upper intervals, 95%. The first treatment level is a little bit higher, second a little bit higher, and the highest nitrogen has the highest mean. And it gives you, but they are somewhat overlapping credible intervals. I mean, it goes from 14 to 21. So there's not like a real strong signal. There's a lot of noise in the data here. So those are the which corresponds to our, the effect being about 3 or 4 difference from the control. It goes up to like 5 different by the time you get to the highest. Now, if you want to get the differences between each pair, because with our parameter estimates, we only had the difference between each one and the control. What if you wanted to know the difference between 1 and 2 or between 1 and 3? You'd have to do all the pairwise comparisons, like a post hoc comparison between each pair of means. So basically that's subtracting them all from each other. Every single, there's 4 levels, so that means 6 possible pairs of comparisons we want to do. You can do that with EM means with a contrast function, and method equals pairwise, which means all pairwise comparisons. So let's do contrast on that, and method equals pairwise. You could also compare each one to the control and that kind of thing, but we're going to do all pairwise. So you can see there's six pairs, and this shows the difference, and it also gives you the credible interval of the difference between each one, which is like our estimate of the effect size. So like, yes, going from 0 to 1, 0 minus 1, the difference is negative, so 0 has a lower yield. But the difference between 1 and 2 is pretty small. It's our point estimate is less than 1 bushel per acre difference, and the credible interval has a lot on both sides of 0. So we don't really have strong evidence here that there's a big difference in between 1 and 2 low and medium nitrogen. So we can say, well, it's probably adequate to fertilize with low nitrogen. In this case, you don't need to add more than that because there's not really an additional benefit. Although actually you do see between 1 and 3, there is a bigger difference there. So you've got that estimate. Now that's the contrast. There are special ggplot extensions that let you plot quantiles of posteriors in any way you want. We can gather EM means draws, pulls them out into a data frame, and then there's special ggplot functions that work with that. I won't explain the code, I just want to show you a couple different ways of how to do it. Yeah, so we use the gather underscore EM means underscore draws function to get the draws out. And then we use ggplot on that post underscore, I called it just post the posterior draws of the estimated marginal means. And this is just one that shows like the full distribution. which is kind of neat. You can see it shows you the median, the 80% and 95% credible intervals, and it also shows you the full distribution. If you're interested in plotting that, it can be kind of nice to show that. It looks like my plotting background reset the options when I quit and came back. So, but that I'll just reset that so it looks like the examples. That's one way to do it. Another way is with the stat interval. So we'll do it with the post EMM draws again. I just wanted to show you some examples of what options are out there for plotting. So this gives you the same data, it's just that the median is now a dot, and then the credible intervals are shown as different shaded bars. This is kind of the way I like to, I think this is a nice summary, and it's sort of concise, and it shows the distribution in kind of like 3 levels of error bar all on top of each other. So that's kind of a nice plot. Does anyone have any questions here? We're getting close to the end here. I'd say in half an hour or so we should cover everything, and then I've saved the afternoon for office hours and everything. So there's not, I see people are starting to get saturated with information, so I don't have too much left. But I'll give you your money's worth and go through the whole thing since you're here. But if anyone has any questions, feel free to put them in the chat. Okay, so we've done everything with just nitrogen, but there was also the phosphorus and potassium treatments, which we've been ignoring so far. I just wanted to show a slightly more complicated model that has the P and K treatments in there as well. Still no interactions between them, but we're also going to account for that N and P, or the P and K treatments. So everything is exactly the same as before, except we have plus P plus K in the fixed effect part. I changed the name of it and changed the random seed. And there is a pre-fit model in the model fit directory, so you won't have to run this. You won't have to wait for it to sample if you're running it on the server. But other than that, it's all the same. The random effects are still random intercepts for site and block. 1 plus N plus P plus K. And then we want a random intercept by site, and then a random intercept by block nested within site, because the blocks are all unique within sites. So this should not have to do anything because it should be preloaded. Yep. So now let's look at the summary of that. Oh, and I would recommend always doing the PP check and plot the trace plots and stuff. I didn't include that in the code because I want to just emphasize that's something you should always do without having to necessarily write it every time. But we could do PP check of this new fit, fix NPK. So yeah, the data are the same. The residuals don't really look that different. We're still not including any random slopes or interactions. So we're still not at a perfect fit to the data, but it's still decent. And if we do the summary, you can see it doesn't say anything about convergence. So that means everything should look good. You can look at the caterpillars on your own if you want to, the trace plots. But now we have a bunch more. We have a different effect for every treatment. You can see now actually our nitrogen coefficients have decreased a lot, and the credible interval got really wide on them because we were kind of averaging over the P and K effects, but I think some of that variation has now been taken up by the P and K effects. But the P and K effects are pretty small. They have their credible intervals go really far on either side of 0. So we really don't have strong evidence that there is much of an effect of P and K, which corresponds with what we saw in the data, that there really wasn't much of an effect. So that's just covering all our bases there. Again, we've looked at we've shown things converge, and the model summary shows that there's not strong effects there of P and K. Okay, so the last model I wanted to talk about today It goes back to, at the beginning, we looked at the plot of the raw data, which showed that at some sites, nitrogen fertilization affected yield, and in some sites it did not. So far, we have completely ignored that in our model. We've said the predictors are the same at the effect of nitrogen is the same at every site. Only sites have different baseline yield, the intercept varies, but we did not allow the model to detect any difference in effect of nitrogen across sites. So we have to add a random slope term to allow that slope to vary, the slope being the treatment effect to vary by site. And we would add that by adding the appropriate slope to the design side of the random effect. So like when we, so far we've had one pipe site, that's just random intercept only. You could add to that random intercept a random slope to allow the nitrogen effect to vary by site, 1 plus n. You could even put random slopes for every treatment, allow the P and the K effect to vary by site as well. You would add that 1 plus n plus P plus K in the parentheses. You could even allow it to vary by block. This is a small data set, and it would kind of be overfitting to do that. So I'm not going to mess with that right now, but you could. There's no reason why you couldn't estimate those as well. So we're gonna throw in random slope for N, P, and K. So the whole model is the same. Again, we're building this up. The fixed effect slopes are the same as we just did. We're gonna have 1 plus N plus P plus K. So let's take a look at what you get there when we do our random slopes. You can see everything else I've put in, but we're gonna put, so yeah, we want to say there's an overall intercept. We still want to put N plus P plus K in the fixed effects to say there's an overall average effect of N, P, and K fertilization across all the sites. But we do want to allow each site to have its own deviation from that, which would catch that fact that we saw that some sites had the same yield more or less regardless of N, and some had higher yield in the higher N. So we'll do that by site, but we're not going to do that by block, because that would, while you could, it would just add way too many parameters to we only have 300 data points, and that adds just tons of parameters. So we're going to just keep a random intercept per block. And anyways, we saw from our ICC that blocks didn't have much variation between them anyway. So this should run from the pre-compiled and pre-fit model. Okay, so let's take a look at the PP check of it, the posterior predictive check plot of that fit. I called it random NPK slopes. Yeah, so it still isn't catching these two humps in the data, but I think that might just be noise in a small data set. So, but it is kind of widening out the bell curves of the fitted values have more variation in them, so they're kind of catching it in a way. Yeah, it is a little bit closer to the data now that we've added these extra parameters. And you can even do the trace plots as well, which is always nice to do. I'll just do them real quick so we can see. And there's going to be a bunch of them because now we have so many parameters. Here's the fixed effects. They all look good. Then we're going to have to just scroll through a bunch of plots. Here are, yeah, there's even more fixed effects because every one has 3. Whoops, session forces suspend. Okay, that's not good. We may have had too many people doing something at once, and it has overloaded our cloud server. I haven't seen that before, so yes, we got 70 people doing this, so it could have hit a limit or something. Well, good thing it happened toward the end. We'll see what happens here. Yeah, but basically, hopefully not too many other people had that problem. Yes, basically I wanted to show that basically the trace plots show the model converged, so we're good there. So now we can look at the estimated marginal means of the nitrogen effect averaged, but now we're averaging over a lot more of stuff. We're averaging over the the P and K treatment effects and the random site effects and everything. So we have, let's look at what it shows us. Once I can get back into this. So yes, I apologize for that. I haven't tried this out before. Having everyone run BRMS at the same time on this cloud server, so it might have just choked on all the people doing it at once. So yes, luckily we're close to the end here. So if we get stuck, we can okay, let's see. I think I need to. I won't try to do too much more complicated. Okay, go back here. Yeah, so we want to do the EM means again by nitrogen. And now what do we see? They are similar-ish to what they were before. We still have a lower mean in the no nitrogen control, but our credible intervals are much wider. It goes from 7 to 20, when before it went from like 12 to 18 or something like that. We have a lot more uncertainty because we're now accounting for the fact that the nitrogen fertilization effect may vary by site. So our estimate of the overall effect adds that uncertainty in, and it's now wider. If we do a contrast of those, using the contrast function of the n underscore em means, and you could say method equals pairwise, but the second argument is method, so you can omit that. If we do n contrasts, you can see actually that there are very high uncertainty in the differences between the treatments, because again, we've allowed the site level variation. So most of the credible intervals of the effects overlap 0, are pretty close to 0. Now, the last thing I'm going to do before we end this is show other ways to test hypotheses that the differences are 0 and quantify that evidence in a similar way as you would get a p-value. And the last thing I want to show from the output is you can use the ranf function to get the random effects, which I just wanted to show how many there are. You can see that there are, look how many parameters this model has now. Every single block has its own random intercept, and it gives you the credible intervals on them. Every site has its own intercept. Every site has its own random slope for adding 1 nitrogen, adding medium nitrogen, and adding high nitrogen, and the same for the 3 levels. So yeah, when you add random slopes, you're adding lots and lots of parameters because you have to add one for every block or every site that you're doing it for. So there's just a lot of parameters in that. Yes. Now, this I will show you how to plot the random effects. This, don't worry about the code. This is just to demonstrate how it looks. We're gonna add predictions of fitted values from the model for each level of nitrogen and setting the phosphorus and potassium to the control for every site. And we're gonna look at those random from the random slopes model and make a plot of it. So yes, I didn't leave any fill in the blanks for this because this is sort of advanced level code. So you can just run it as is. Or just watch what I do if you don't want to run it. Yeah, so here are the random slopes by site. These are the modeled predictions, and then I put credible intervals in a green shaded thing. So you can see that some of the sites have basically no effect, and some have difference between low and high, and the model is actually catching that now. This is not the data, these are predictions from the model. So you can see it kind of looks a little bit like our data, where like the ones that had a high difference in yield, the model is now capturing that random slope. Any questions? Okay, so that is Basically, another point to raise about mixed models is that you have what's called shrinkage, where you're not just averaging out the raw data and looking at the differences. The trends within sight are less extreme than the raw data. It's shrinking those estimates towards zero, toward the mean, which means you get better predictions you're sort of sacrificing a little bit of the good fit to the data in exchange for being able to predict better on new data. Like if you found a random site, you know nothing about it, you don't know whether it's going to be a site that has really high effective nitrogen or no effective nitrogen. We know it's just a new site that we know nothing about. So our prediction for that new site should kind of be somewhere in between, a little closer to the average. That allows us to get better predictions for new data, even though it makes the model fit the data a little bit less perfectly that we have. And that's something that happens in all mixed models, not just Bayesian. That's what you want. And I just want to also mention, even though we're not going to do it here, that you can put interaction terms into your fixed effect by putting N:(P) means two-way interaction, and asterisks mean all possible interactions. So N*P*K would be all one-way, two-way, and three-way effects of N, P, and K. If you really still want to play with this, feel free to make models with interactions and play with them. Okay, so two more things to talk about. One is we've done all these models. How do we know which one is the best fit to the data? We can use sort of like an information criteria approach, kind of like AIC, but there's a special information criteria for these models called LOO, the leave one out information criterion. And it basically gives you're fitting the model to all data points except one, and then predicting that data point, doing that for every data point and seeing how well the model fits. And that's going to give a better score to models that are a closer fit to the data without being overfit, without having too much parameters for the data. So what we have to do is we have to use the function add criterion to compute that information criterion for every model, and then compare them to rank the models. So we add criterion for all. I'm going to do the intercept model that we did, the one with just nitrogen, the one with NP and K, and then the random slope model. Those are kind of like the four models we fit today. So let's compare them all. We use add_criterion. Hopefully this won't kill the server and everyone does this. Maybe I'll do it first, and then everyone else can do it. So if we do add criterion and then use the LOO as the second argument of which criterion, I'm going to highlight that and then run it for all the four models. It will give some possibly warning messages, but yep. And now if we use the function LOO_compare, which will compare the information criteria for all the models. It'll put the best one at the top with 0 and rank the other ones relative to that. So here we see the random slope model is the best fit to the data. Despite having the most parameters, it is the best fit because it's capturing that site level variation in effect that the other models ignored. The other models are 20, 21, and 51 information criteria units worse. So they're a much poorer fit to the data. It gives you a standard error of the difference between them as well. So the difference is 20 and standard error of the difference 8. So we can say that the random slope model is a better fit. And you can see that the intercept only model that left out all the treatment effects is way at the bottom, which we would expect because there was a treatment effect. So this means we can say, even though our random slope model had more parameters, it's justifiable to fit that model because it's capturing something that's really in the data. Okay. Now the final section of this before we quit and go to office hours is to look at ways to talk about hypothesis testing in Bayesian models. Like what will you put in your manuscript to look at, like, in where you would put a p-value from a frequentist model? There are several ways to test hypotheses with the Bayesian model that you could report to show the strength of evidence for and against there being a treatment effect. One of them is a Bayes factor. That is the ratio of evidence between two models. And basically, it can be from 0 to infinity. Bayes factor equals 1 means the two models have equal evidence in favor of them. Greater than 1 means model 1 has more evidence, and it could be less than 1 as well. And some people, since you like to have like a p is less than 0.05 kind of analog, like to say, well, Bayes factor greater than 10 is the new p is less than 0.05. It means there's significant, if you want to call significant in the Bayesian sense, evidence for an effect. I see there are some questions in the chat, so let me take a break and address them. There seem to be some R questions. Hopefully we can revisit those later, but there's a more conceptual question. At what point would a model be good enough? Complex models are always better than simple ones, right? Well, I would say no, because once you have reached an overfitting level, then that model is overfit to your data and it will not predict as well on new data. So I would say the best model is one that predicts best on data that wasn't used to fit the model. So you need to have it be complex enough to capture whatever's going on, but not too complex that is just fitting on noise that's in your data. If you accidentally think that noise in your data is a true pattern, that's overfit to the data. So you want to strike that balance. And it seems like, well, since I picked this data set to illustrate the random slope model, that was the best in this case, but that won't always be the case. Sometimes adding random slopes will make it predict worse. And then you would see that in the cross validation. So yeah, you kind of have to make it as complex as it needs to be. Occam's razor, Yes, so there's a package called, yes, let's finish up the last couple things. The package called Bayes test R, we're going to use the rest of the time. It can give you Bayes factors for individual parameters in your model. And the way we're going to do it here is it's the ratio of posterior evidence to prior. And if you remember, our prior distribution said we're normal mean at 0. So that's kind of like a null hypothesis. So when we do these Bayes factors, it will be kind of like we're testing a null hypothesis. We're kind of bringing the frequentist back in by testing a null hypothesis that there's no difference. If Bayes factor equals 1, that means we did not change our belief about the parameter after we saw the data. And since our prior was a null hypothesis, if our Bayes factor is 1 or less, we can say that there's not evidence that the parameter is different from a null, basically. If the Bayes factor is bigger than 1, we do have evidence that the data has changed our belief from the null hypothesis that we had before to a new belief that there is an effect. So let's see what we get. Well, we have to basically resample the priors of our model using unupdate to sample the priors, then calculate the estimated marginal means for the priors, and then compare them using Bayes factors. So we make our contrasts again using the priors and compare it to the contrast we got from our posterior. And that will give us a Bayes factor for each of those 6 pairwise comparisons. So let's do that. So we have to unupdate, which means sample the priors of the model. And then we have to do our EM means again. So basically, yes, we got these. If you go back, we had, if you scroll up in the output, oh, there's a lot here. These are the contrasts, the model predictions of our posterior estimates of the difference between the treatments. We want to do those same contrasts in the priors, pretending like we never saw the data, then compare them with Bayes factors to see which one has more evidence for them. So let's run that. It'll resample the priors. And then we're going to use the function Bayes factor underscore parameters. And our posterior is going to be the n contrasts that we did before. And our prior is our n contrasts prior that we're doing right now. So once this runs, which takes a second, we can then calculate the Bayes factor for each of those 6 pairwise comparisons. So hopefully we haven't abused the server too much. Okay, so we sampled the priors and then it calculated the contrast based on the prior. Now we're going to do the Bayes factor on those. And so it says, warning, Bayes factors might not be precise. For precise Bayes factors, sampling at least 40,000 posterior samples is recommended. So that just means you really need to calculate the tails of the distribution well, but in this case, that's just a sort of default warning that pops up. I think what we have now is good enough. So what do you see here? The Bayes factor is less than 1 for all the differences except the difference between 0 nitrogen and 2 nitrogen. The Bayes factor is 8. So if you look back at the contrasts, you can see the difference between 0 and 2 is about 3.8 bushels per acre. The credible interval does not overlap 0 there. So it's like, well, that's the one we'd expect to have the most evidence that the effect is non-zero. And that's exactly what we see. The rest of them, the effects are pretty close to 0. And that's why the Bayes factor says we have just as much evidence that the null of 0 is true as we did before. So we didn't change our belief that the null hypothesis or that the prior with mean of 0 is true. But for this one, we did. So it's like, okay, adding medium nitrogen seems to be effective at increasing yield. We have decent evidence. The Bayes factor is 8. I mean, it doesn't reach the Bayes factor of 10, but it's kind of just another independent line of evidence we can use to say that there's a moderate evidence for a treatment effect there. And there's even a couple of other ways to get, you can see we've now reached the very end of the code. So we are now just about done with that. So there's a couple other Bayesian p-values you can calculate that are actually look like a p-value, or it's a value that ranges between 0 and 1. The lower it is, the more evidence for a difference. You can actually do that because I know people like p-values. Oh yes, and I just want to mention that Bayes factors are very sensitive to your choice of prior as well, because it's actually using the priors to calculate them. So another reason to try out different priors would be to make sure, do a sensitivity analysis and make sure your Bayes factor doesn't depend too much on that. So yes, the final bit of this is there are also a couple of different p-value style numbers that you can calculate from a Bayesian analysis that will tell you the odds against the null hypothesis. So this isn't your prior anymore. You have to actually set the null hypothesis to, for example, 0 contrast, a difference of 0 between yields is your null hypothesis. So there's p point null is a function in the Bayes test R package that will allow you to specify, put in your pairwise differences that we calculated, and then a null value, and it'll calculate essentially it'll compare the posterior that you got to 0 and see what the ratio of probability is. If the ratio of probability of the null to what you got is very low, it'll be close to 0. It's kind of like a p-value. But it's called the maximum a posteriori p-value. So we put null equals 0. Run that. You see it comes up with a fairly similar interpretation of the Bayes factor. The map p-value is 0.01 for the difference where we saw the biggest difference, the rest of them are close to 1. So that's just another corroboration that the one we have the most evidence for is that particular one. And then I just want to show one more, which is there's also the ROPE, the region of practical equivalence p-value. We don't have to test that it's exactly 0. We can define a range that is scientifically or practically relevant for effects that we think are biologically significant. Like let's say you figured out how much fertilizer costs and it would be worth it to buy fertilizer if the yield increase was 1 bushel per acre or more. Well, you can put in sort of a region that you would consider to be practically equivalent. So anything between -1 and 1 yield difference is practically equivalent. And you can say, what is the posterior probability that that effect is bigger than, is outside of that range? And you can get a p-value like number for that as well, the p-ROPE. So we'll do a p-ROPE. And the range goes from -1 to 1. And you get the same, yep. So again, a similar interpretation to the other ones where the probability that the proportion of samples that are between -1 and 1 is only 1%, 0.01 for the one where we saw the biggest difference. It's a lot higher for the ones where we didn't see much difference. It has a similar interpretation. Yes, I see there's some questions in the chat. I will get to that in just 1 second. But let's say we decided only half a bushel per acre was enough to justify. So we said, okay, maybe it's practically equivalent only if it's 0.0 or 0.5 or less. So you could do any range you want there. Let's look at that interpretation. So now you see the sort of p-values go down because we said a smaller effect is still biologically significant. So actually, some of the other ones are getting closer to what we would interpret as evidence for a difference because we put in a narrower range of equivalence. Yeah, so ROPE is kind of nice because it's not as sensitive to your priors or your methods, but it's completely dependent on what you set as what you consider to be practically equivalent. So, you know, definitely be explicit about if you report that, you would want to probably do it for a range of effect sizes that you consider practically equivalent if you were putting it in a paper. Yes, so let me check the chat here. Yes, what did the unupdate function do? Yes, so it looks like Grant answered that. It drew samples from the prior distribution. Yes, so what we did was we resampled the model without using the data. We only resampled the prior distributions. So then we have a prior distribution of our pairwise differences using our sort of null priors. And then we have a posterior distribution of our differences that is the combination of our priors and the data we observed. So it's like our new beliefs after we saw the data. Then we see if those beliefs changed enough to warrant actually saying it's a different effect than the null. And we only see that in some cases and not others because some of the effects they could be 0. That means we based on the data, we didn't see anything in the data to tell us that adding low nitrogen was different than no effect at all. So that's once we did the random slope model. So thanks for asking that. Yes, so let me see. I believe this brings us to the end of the content. So I wanted to let you all congratulate yourselves on all the stuff you've learned today before we open it for Q&A. So let's revisit those learning objectives and see what we learned today. Well, maybe you learned this and maybe you didn't, but the idea was that you have now had some exposure to at least the basics of Bayesian inference and how it works. Now, if you're at a cocktail party and someone's like, oh, the prior was this, but the likelihood and posterior was this, you'll know exactly what they're talking about and you can join in that conversation without feeling like you don't understand it. And Markov chain, you're good with that now.
We're usually about cocktail party.
Yes, maybe it's not the most, rockin' party, but yes, okay, and then the credible interval, as well, we've gone over that. And practically, you're doing great because you can now write BRMS code for a multi-level or a mixed model with random intercepts, even random slopes. You know what it looks like when a model converged and when it didn't, and how to maybe do something about it. You can interpret the output. You can compare the models to see which one is a better fit to the data. You can use different indexes of effect size, like Bayes factors and p-values, to look at the evidence, and you can even make some plots. Or at least you've seen it done one time, which is a good start. Because this is the kind of thing that takes years to learn. Oh, and now you can print up this sign and post it up in your front yard because you're now a Bayesian. And I won't read it out loud, but yeah, that is basically, you now have started your journey of becoming Bayesians, maybe, which is cool. So give yourselves a round of applause. Yeah. All right. Definitely. Okay. And before we open it for Q&A, I just want to I made a feedback form, if you wouldn't mind filling it out. That would be very helpful for me to make these offerings better. I'll put this in the chat. Since you can't click on that, so I'll put it in the chat. You don't have to do it right this second, but whenever you get the chance, it would be great. I guess people that are local, you might have to copy that down, but if not, too long of a URL. So yes, and that is it. So here's what I'll do. I will answer questions for a little while, and then take a lunch break, and then I'll get back on at 2 p.m. Eastern, 1 p.m. Central for any more office hours. If folks have any more questions or wanted to run over some stuff again, I'm happy to do it. But thanks to everyone for participating, and thanks again to Grant and Amanda for helping out with the technical side of it. Yes, thanks to all of you. So yeah, any questions? Or did I deaden everyone's brain and people just want to go have a lunch break? I understand that. Yes, and as a reminder, once I get the recording uploaded, probably next week at some point, I will send out a link with the video recording that everybody can get. So yeah, I'll have that. Yes. Oh yeah, did I want to talk about the relationship between the trace plot and the posterior draws? Yeah, we can go back to that one more time if folks, just as a good reminder, since we did have a lot of questions about that during the thing. Let me see if I can go back to those trace plots at all. Yeah, so these basically whatever's on the right side is the trace plot, and the left side is the distribution, but these are the same data are used to make each of these. The trace plot just shows it in order of where the samples appeared in the sampling, which you don't actually care about that for your statistical inference. It is only a diagnostic to make sure the model converged. You only look at this. You wouldn't publish this in a manuscript. Like in my manuscripts, when I publish the results of these, I say, convergence was assessed by examining trace plots and R-hat statistics. You wouldn't, this does not tell you anything about the model results. It's only a diagnostic to make sure it converged. This is a little bit more getting you towards that because it's actually showing the posterior distribution of our parameter estimate. So in this case, it's the effect of adding medium phosphorus compared to the control. You see that it's pretty much close. It's not a big effect because it's near zero and has a very wide uncertainty. So that shows that distribution. But I would not necessarily put this in the figure in a figure either. I would just use a figure showing the median and credible interval as we do here, for example. Yeah, so people are still having issues with the R. Yes, I see that there's lots of, yeah, if you don't mind, I will, if we have more kind of like conceptual questions, I will answer them now, and then if you want to, get back on this same Zoom at 2 p.m. Eastern, I will do more of the troubleshooting stuff one-on-one with anyone who wants to do that. But yeah, so but I'm happy to answer more general questions now. Oh, I should stop the screen share too. Yeah. Well, it seems like there's not too many other questions, so I will in just a minute shut off the Zoom, and I see people are starting to leave, but I really do appreciate everyone who participated. Thank you.